Okay. On the record, we initialized these simulations as a gas disk with a single magnetic field loop and 10 to the 8 solar mass supermassive black hole located at the origin. Then we evolved the ideal magnetohydrodynamic equations coupled with radiative transfer equations until we reach a steady state where we have a dense optically thick midplane surrounded by this lower density region where the density drops off with height above and below the midplane at 0. And you'll notice from the way that the gas is moving around in this movie and from the way that the velocity vectors are kind of crazy, that this gas disk is turbulent. And I want to be really clear on the record that we do not prescribe this turbulence in any way. We don't set it. It's just what naturally evolves from evolving the equations of radiation and HT. And so because we have a magnetized disk, we just naturally evolve to be magnetorotationally unstable. So we get MRI, which is actually what drives accretion in this AGN disk at about 10% Eddington. And then we also drive convection because of the density and temperature structure of our disk, setting the opacity of our disk. And you can actually see this convection as sometimes, especially below the disk, you'll see the little velocity vectors go in little circles. That's convection. And that's actually what puffs out that bottom of the disk. Okay, so just like my previous shearing box simulations, in these now global simulations that go all the way out to 250 RG, I'm going to use two different wavelength groups for my radiation. The first wavelength group is going to be a long wavelength group. So that's now what I'm showing instead of the velocity vectors. I'm showing the vectors of what is really UV flux. For this radial range, we really go all the way from the far UV into actually we've reached the G band. So we're now in a Rubin waveband all the way out to 250 RG. But so this first wavelength group shows the long wavelength group, which tracks the local black body emission. So you can see the disk emitting from the flux vectors there. And then the second group is going to be that short wavelength group, which we're going to use to inject X-ray irradiation in from the simulation boundary as if it is coming from a corona at a cylindrical radius of 10 RG and a cylindrical height of 30 RG. So now we have some geometry, unlike in the shearing box simulations, for this corona. And again, you can see the X-ray flux coming into the simulation box and irradiating the disk. And so one thing to note is that we're actually going to analyze both faces of the disk, the top and the bottom, individually, so above 100 and below 100. And that's because usually when we observe these kinds of AGN disks, we're observing them mostly face on. And so you would really observe these as two completely different AGN disks. And so first, we're just going to focus on the top of the disk. And so what's cool about the top of the disk is if you focus in the right panel, I should have said before that the solid red lines are showing the photosphere, so where the optical depth is 1. And in the right panel, it's showing the UV photosphere. You can see that the UV photosphere is pretty low down. The disk is pretty thin. The density drops off quickly. And so you have this thin disk. We're actually going to see that this thin disk behaves just like the lamppost model. It looks just like our traditional reverberation mapping model. So right, you look at the X-ray flux, it comes in, it gets absorbed in the X-ray photosphere, and it gets re-emitted as UV emission. And we can see this when we look at the X-ray and UV light curves. So now we have many radii that we can collect light curves from. So I'm showing the X-ray light curve, which I rescaled for comparison in gray. And then I'm showing 6 light curves we take from the simulation that come from 6 different radii. And you can see that for all of these radii, the X-ray and UV light curves are pretty well correlated. There are some exceptions, which I'm very happy to talk about, but for the most part, these are very strongly correlated light curves. You can also tell this by looking at the power spectrum. So the colored dots are for the different radii light curve PSDs, and then the solid gray line is for the X-ray PSD. And again, you can see that they're pretty consistent and that X-ray light curve is really setting the variability in the UV light curves that are emitted. And then again, we can now do reverberation mapping as a function of radius. And so we do that from the top of the disk here. And so if you look at the left panel, we use 2 different reference bands. First, we use the X-ray light curve as a reference. Those are the diamonds. And then for the circles, we just use the innermost radius UV light curve as the circles, which is at 34 RG. And the dotted and the solid line both show the light crossing timescales for the 2 different reference bands. And you can see that the lag is a pretty good match for the light crossing timescale. And so this is really great because that's what it should be. And if you look at the right panel, we show the correlation coefficient from these lags, which are calculated using a cross correlation, right? So if you look at the maximum correlation coefficient for these lags, you see that they do decrease a little bit with radius, but they stay really high. They're very strongly correlated above 0.85. So all of this looks a lot like our just standard models for reverberation mapping. But then we have our problem child, which is the bottom of the disk. So I'll leave the top exposed so you can compare, but you can see very clearly, right, the density drops off more slowly from the bottom of the disk. The photosphere, that red line, is much more puffed out. It's much further down from the bottom of the disk than the top of the disk. So now we have kind of a thick disk with a bit of an outflow. And you can actually see, if you look at the field lines, you can actually see the UV flux is behaving differently from the top and the bottom of the disk. In the top of the disk, it's mostly emitted like vertically, right, like straight out in the positive Z direction. But for the bottom of the disk, at a lot of timescales, it's really kind of moving very radially, and that's because it's optically thick enough in the bottom of the disk for the flux to really be advected along with the flow. And so we really already see that this is going to produce different behavior. And when we look at the light curves, again, I've rescaled the gray light curve, the X-ray light curve for comparison. You can see that, especially as you move outwards in radius, the light curves are no longer as well correlated. When we look at the power spectrum of these light curves, it becomes really clear that at higher frequencies, the X-ray and the various UV PSPs are distinct from each other. And the big reason for this is because they have this bending timescale. So we fit a bending power law to all the different PSDs, and you can see in the legend is our best fits for the different PSDs. And we very often fit these bending power laws to AGN light curves. And the bending timescale has been thought to maybe represent the thermal timescale of the disk. And when you actually fit these bending power laws to our simulated light curves from this bottom of the disk, you can see that the bending frequency decreases with radius, or that the timescale increases with radius, which is what you would expect, because the thermal timescale, all the timescales really should increase as you move further outwards in the disk. And so we actually find that this bending timescale is a pretty good match for the thermal timescale at each of these radii of the disk. So all of this is just really showing that there's some sort of disk physics that's impacting the UV light curves emitted from the bottom of this disk. And then the final thing I can show about this is that the reverberation mapping as a function of radius for now the bottom of the disk. So again, we use two different reference bands, our innermost emitted light curve at 34 Rg and our X-ray reference. And if you compare to the dotted and the solid line, which both show the light crossing timescales, you can see that in both cases, as you move outwards in radius, the lag becomes longer than the light travel time, very significantly in the X-ray case, but still even in the using the UV reference band case. And if you look at the right panel, now the correlation coefficient for these cross correlations drops off really rapidly with radius, all the way down to 0.2. So all of a sudden you have longer than anticipated lags and poorly correlated light curves, which of course is a big departure from the lamppost model, from traditional reverberation mapping models. However, is actually really consistent with a lot of recent observations. I mean, Marcin was talking about one yesterday. I think Zach will probably talk about this later this week, right? We're seeing a lot of lags that are longer than predicted by the light travel time. And we're seeing a lot of poorly correlated X-ray and UV optical light curves. And very commonly, there are a lot of models that try to explain this, but a very common one is contamination from diffuse continuum from the broadline region. But again, these simulations have no broadline region. And so that is not what's going on here. It's actually the disk structure that leads to this behavior. So I'll just really quickly, with the time I have left, try and give a little bit of a physical interpretation of what we're seeing here. So again, if you look at the top of the disk, the X-ray radiation comes in, it reaches the X-ray photosphere, gets absorbed, it gets reprocessed, it gets re-emitted. Lamppost model. If you look at the bottom of the disk, you can see that because the density drops off more slowly, if you look at the color of the X-ray flux that's coming in, you can see that it often turns blue. such that which signifies that it's being absorbed before it reaches the X-ray photosphere in the outer disk. And so what happens, we think, is that the X-ray irradiation is being absorbed in the inner region of the disk, which emits in the far UV, and then that far UV emission is moving outwards along the disk and being reprocessed out farther in the disk in the UV and the optical. And so you're having this additional reprocessing step, which can mean that it takes longer for the light to travel because it has to be reprocessed multiple times. In addition, each time this light curve is reprocessed, there's some intrinsic variability driven by disk fluctuations that gets added to the light curve, which lowers our correlations. And in addition, this intrinsic variability has its own lag. So as I was supposed to talk about today, it has this lag that is produced because these fluctuations are propagating, and this can be a confounding signal. And so I should say, in our simulations, we can actually see these fluctuations that are impacting the emitted light curves, and we can actually see them being propagated through the disk. So what I'm showing here is a slice of my disk at a polar angle or a specific height below the disk. And if you look at the density fluctuations, that's what the color is showing as a function of radius and time, you can see these repeating patterns that are actually being propagated inwards at this inflow speed that we fit with that solid line. This is actually a really good match from some observations of local AGN done by Jack Moonstad and Chris Kuchenik. And the final thing I'll say, because I'm out of time, is we can actually measure these lags in our light curves. So I'm showing a cross correlation where we use that innermost radius light curve as our reference band, and you can see that both the cross correlation and when we look at the phase of the cross spectrum using this Fourier method, both kind of predict this 1,000-day lag that, again, we can see in our data. So I'll leave up my summary, but the take-home point is that this variability that's driven by these fluctuations in these disks can produce a lot of the things that we're observing, and that it's disk structure alone that can actually lead to these departures from traditional reverberation mapping. So, thanks.
Very much. Questions? You, let's see if
Hi, thanks for the nice one. I wonder what causes this asymmetry between the top and bottom of this.
Yeah, so thank you for asking that, because so what happens is when we initialize this disk, it's initially turbulent, and there are just some fluctuations that can grow over time that produce this asymmetry. But this simulation, to do this analysis, I ran for about 10 years. But the overall run of the simulation is about 1,000 years. And over 1,000 years, this disk structure doesn't stay constant. So for these 10 years, it does. But the disk does change and evolve over time. And so this is actually completely stochastic. So, we don't claim that thin disks or thick disks are more or less common. We don't claim that asymmetric disks are common. All we claim is that both are stochastically possible and produce these results. So yeah, statistically, we don't really make any statement on that. Yeah.
I have the same question. So
Yeah.
I don't understand that in practice. You should see, if you see the disk from above, it should be broken. But if there would be no agreement.
Yeah.
And labs will.
Yeah.
I don't understand. For all the data that we've got.
Yes.
Do you then say that we see the disk from the bottom all the time?
Oh, so it isn't, again, like it's not guaranteed that it's a top or a bottom, and it could be both sides of a disk. So this is kind of just a random thing that happened in this simulation, which means it's both are possible. So one goal with what we've done here is we've done a lot of analysis of these light curves. And so we're hopeful that maybe we can actually be able to predict if an AGN has a puffed up disk or a thin disk based on their light curve. But yeah, so all this is I'm trying to make sure I'm explaining it well. But It's just a stochastic fluctuation that for this period of time, we see the disk looking like this. In a different period of time, it would look like something else, or a different initial fluctuation in the disk would cause a different random thing. So we could see any kind of disk out there. What's nice is because the simulation is like this, we can use that to try and determine what the disk that we look like, that we observe in real life is actually looking like. So that's the goal.
Thanks for this nice talk. But the observed AGN lag spectrum does show atomic features.
That's sorry?
Atomic features in the observed lag spectrum. So how your model is going to explain the atomic features, like the mountain?
Sorry, one last.
How are you going to explain the mountain in the lag spectrum?
Oh yeah. So I'm not saying that the broadline region isn't having any impact, right? I think that would make sense as being responsible for the Balmer jump. So I'm not saying it has no impact. I'm just saying it isn't the only reason we can see this. And I think the Balmer jump in particular is that broadline region. I just think some of that optical and UV extension not around the Balmer jump could be disk structured, and there are observational reasons. I actually think that I probably can't get into now, but I'd be happy to talk about it after.
Thank you again very much. Second talk. When LSST meets spherics. Important.
Thank you. Hello everyone. My name is Heraklion. I'm from Heraklion. I'm going to tell you about the LSST and the SphereX. So which is, I didn't bring any serious science, but give you some sort of the flavor. If we have LSST and SphereX, then what we can do. So this is motivation. The game started. So we will have the DP2 very soon, within a couple of months, and the DR1 is scheduled to be released. So it's good time to thinking about how we construct the AGN from the LSST observation. But then we have challenges, especially to use the data from the early operation. The one, AGN selection. This illustration from the Agile paper clearly tells you there is the confusion between the type 2 AGN and the stars. I mean, there is color space. There are specific locus in where the stars are located, but still, I mean, the stars are often confused with the galaxy, with the AGN with the galaxies. Especially if you have a U-band, it will have a little bit, but we still need to color selection is not robust to the stellar contamination. Second, redshift. This 3 panel shows you the standard deviation and the bias and the outlier fraction of the photo Z compared to the spectroscopic redshift. And there are 5 lines, but clearly see the blue and the yellow line versus and the green, pink, and red lines. Blue and the yellow lines have it based on the LSST 10-year operation, so the full data set. And green, pink, and the red lines are based on 2 years of the LSST operation. So clearly it tells you we need the full 10-year LSST operation to get a better performance. But to see more closely, I mean, the yellow line versus the blue line, for example, tells you if we have the Euclid, which is the yellow, we will have a little bit better performance in terms of getting the photo Z the redshift, because Euclid have a neon the UV photometry. So we need the full LSST and the UV. So it's a bit difficult now, but I'm going to tell you the spheres can solve both for the limited the magnitude limited sample. SphereX is launched in 2025. This is the little capture figures that I captured from the real time of the launching. And the SphereX is operating on the plot on the left top. So it scans the sky according to the ecliptic. It scans the sky, but the detector itself has a linear variable filter. So that means same object in the sky is located the different positions of the detector. Different positions of the sphere's detector means that the different filter. It has 102 the channels. So same object as you illustrated in the figures, observed in the multiple times in the different the wavelengths. So you got 102 colors of the same object. So sensitivity of the SphereX is look like in the plot on the right hand side. It's the yellow is the old sky and the red is the deep survey. Deep means that there is two regions of the sky, the south and the north pole, where the spheres scans multiple times. So it has the deep observation, but the mostly all sky. This is sort of the depth of the spheres. So summary from the 7,500 angstrom up to 5 micron, it has the spectral resolution, pulse resolution, wide field of view, and the 10 AV magnitude is a sort of sensitivity. So it produces a complete spectra over 6.4 seconds of the whole sky. Right. So what I do is I go to the object from the DP1 created by the Niel et al. Of the QSX catalog. So it has produced the 1,456 object from the DP1 and cross-matched with the 4 existing AGN quasar catalog. So this is AGN or the quasar. So I just get the photometry from the spheres for those objects located in this region on the left-hand side, the sky region of this DP1 field. Then this is the example of the spheres and the spectral photometric data. So if you specify a coordinate, it will give you this spectrum. So this is the force spectrometry at a given position using the empirically constructed PSF model. This is not a catalog of the spectrum. This is a real-time job based on the pipeline. So it has the bunch of flagging information encoded a bitmap. So 2 options, point sources versus extended morphology, that gives you different the spectrum. So in this study, I just assume everything is a point source. So these example 5 channels are shown as an example. There are many more channels, but it is a clear detection. Right, then I have to do the extinction correction based on the red map and the Milky Way extinction curves. So some of the DP1 regions actually in the galactic planet, so the extinction is quite significant. Then I have to worry about the LSST photometry. There are multiple PSF flux and the aperture photometry, from flux, and the C model flux. Each has its pros and cons. PSF flux is only good for the QSO, but not good for the host galaxy with the AGN. Aperture photometry is a fixed aperture, so again, it's not good for every galaxies. And the chro magnitude is adaptive aperture, so it's good for overall, but good for the getting into total magnitude. And the C model flux is also good for the galaxy particularly, but if it's not ideal for the type 1 quasar. So for this exercise, I tried multiple things, but I ended up using the chron flux as the sort of not optimal, but sort of the best choice. This is I'm going to show you some examples of the spheres and the data, and the key feature is the H alpha and the H beta emission. H alpha is the primary spectral feature, and H beta is also visible. And the plot on the left-hand side shows you LSST photometry as the circle, and the blue and the red is the sphere photometry, but both in the before and after the extinction correction. It is very useful for the clear distinction between stars and AGN. For example, plot on the right-hand side is the spectrum from the M-dwarf stars, and if LSST stop at 1 micron. So if you keep the photometer from the LSST, if you don't know anything beyond the 1 micron, this spectrum is confused with the LSST AGN. So it's very good to have the spectrometer, the spectrum up to the 5 micron, and also very useful to confirm the redshift, either spec Z or the photo Z. So these are the typical several examples. If you have the line emission, you can confirm the redshift very easily. The left-hand side is an example of the incorrect redshift. I mean, these catalog have the photo Z or the spec Z, but not everything is a spec Z. But if you have based on the LSST photometry, if you add the spheres to spectrum, you clearly see the H alpha. You can see that this is not a quasar from the redshift 0.1. This is much higher than that. And on the right-hand side, it's a correct case. I mean, the redshift at 2.6 is roughly consistent with the sphere spectrum. So both useful. Either we have a line or no line. And this is an example of the high Z AGN of quasar. This is actually the G-band dropout galaxies. And the plot on the right-hand side is the LSST L-band images, and the little red square box is the 2.6 2-arc second sphere pixel. And there are faint smudgy galaxies in the middle. And this sphere, on the part of the left-hand side, Spherix spectrum shows a H-alpha emission, and which is consistent with the spectroscopic regression. And this is already recognized by the other group. So already published a paper based on the 300 Gaia Y selected QSO. They checked this Spherix spectroscopy. They confirmed the high Z QSO, the quasar and AGN redshift greater than 4. So we can do the same thing, and that clearly we are not alone. And this is another example of the very faint galaxies. You will not be able to see any existing database, but if you look at the LSST and the outband images, there are very faint features there in the center. And this turns out to be the emission line galaxies that are the 0.74. It's detected in Chandra Deep and South. Spherix, this H-alpha feature is, it's visible. Clearly it's not a noise. So this is the galaxy, the emission line galaxy can detect. But this is more tricky case. I mean, there's the continued mismatch between the Spherix and the LSST photometry for this object in the center with a very bright nearby object. So overall spectral feature is is still there, but the overall continuum spectrum is off from the IGN photometry. So Spherix photometry is really contaminated by the very close nearby stuff, while the LSST photometry is fairly robust. And again, same example. And this is the opposite case where the galaxy, host galaxy itself is very extended. The Spherix the data is underestimated overall flux, while the LSST based on chrome magnitude, the adaptive temperature, we get the total flux from those galaxies. Again, you see the continuum of the mismatch between these two. This case is a similarly extended galaxy, but the Spherix, the LSST SED have a pretty consistent, and it has the 3.3 micron pH emission as well. But this is a pretty the challenging case. So let's just assume without knowing anything, we don't have any existing data set. We see this object and we look at the spectrum from the LSST and the Spherix. This is quite similar to the stellar spectrum, but still no emission, and so it's very difficult. But if then we need a morphology information from the LSST images, and we're checking other actually the radio data from the sky of the Gaia, then we may be able to confirm this is an AGN, not a star. So this is again one example. LSST broadband photometry is aligned with the H-alpha emission line, so it's broadband photometry might be just contaminated for certain case. And this is a bit of an absorption, I don't know, but the Spherix has this beam splitter. So around the 2.4 micron, there is the pixel we cannot really use. Although I flag those pixels, I still see from some cases like this spectrum. Okay, so the to-do list. I need the best match photometry for LSST and the Spherix. And we also need to have a correct or ignore the spatially blended the sources. And have to test the photos with them without the Spherix data. So then we need to compile the multiple data as well. The plan is to publish this result as a proof of concept paper. We continue the exercise this to prepare for the DP2 and the DR1. So the companion of the project is to work with the Agile team to simulate the LSST and the Spherix photometry based on the simulated spectrum images of the AGN population. But I'm going to highlight that we already have a very good nice set of the multi-variable survey data. All the red text indicating the X-ray, Evo-zeta, with the 25%. Optical neural, there are many, but not all sky. But the middle we have a WISE, and the file we have Arcari, and the radio we have EMU, and the VLAS. So these are the sort of the footprint area for the DP2 and the DP1. We can do many things because these areas overlap with the major surveys, like the dark energy survey, and these Subaru and the kids, and the Euclid now is available, and the Atacama Cosmology Telescope has a fairly wide coverage of the sky. So the radio is very good as well. This is the EMU survey. I mean, the gray area is already completed region of the sky, but the empty square is actually TBD. So they need about roughly 50% completed in the sky. VLAS is already completed for the 4 epoch, and everything beyond the minus 40-degree sky is fully covered now. So we have a very good coverage in the X-ray and the radio as well. So the last final slide that we are also going to do is the agile population 1 and 2 ATNs up to 2 pressure to 5.5 and the full SCD, QSO ATN SCD. So we're going to spectrometry and try to figure out the selection function, characterize the performance and the photos using a simulator data as well. Yeah, so the last goal is to construct the brightest AGN phasor catalog by combining LSST and spares. Magnitude limited, but we will be able to understand what's the limit of the magnitude if you want to add the spares spectrometry. So we'll be a high purity AGN catalog with the accurate version without the needs of the spectroscopy follow-up. Yeah, so this is what I'm going to say. Thank you.
We have time for one question.
Hi, Ilson. I have a very practical question that I have used the spares, but how feasible is to get the data from spares?
How feasible it means how quickly?
How quickly, yeah.
Yeah, it's a very slow now. So I have this the URSA only digested 20 per request. So I have to manually truncate the 1,400 ship 2020 and almost keep up with it together. So it's a very slow manual process. So this is definitely not feasible. So I'm just actually talking with the spares team for the collaboration. So probably without waiting until they release the full catalog, probably we'll be able to get the data and be able to the list of the candidate from the LSST. Definitely, this process that I'm demonstrating showing you is not what we are going to.
Okay, thank you very much. Then, oh. Yeah. Rebecca, can you hear us?
Yes, can you hear me?
Yes.
Yeah.
So, see your screen. Okay.
Okay,
So,
all good?
go ahead. Go on.
Okay.
Sorry. I'll introduce you next up, Rebecca McRoy on extreme long variability of my brand.
Ja, dan denk je niets te gaan eruit. Maar niets te gaan eruit zijn gezongen.
Yes, that's okay. Please take it away.
Okay, go. Hello, hi. I realized yesterday I forgot to introduce myself. Hello, my name's Rebecca McElroy. I am a lecturer at the University of Southern Queensland in Australia. Really sad I'm not there with you. I bet the weather is a lot better where you are. But today I'm going to talk to you about my favorite changing look AGN, Marcarian 1018. I will highlight first that this is work by me, my PhD student Thomas, and several others. So we all love changing look AGN. This is a phenomenon that is further and more than typical AGN variability, much more dramatic, causing brightening or dimming by large factors, and in particular, changes between observed optical spectral types. So we observe things to transition between type 1 and type 2, gaining or losing continuum emission, and gaining or losing broadline emission. To be honest, I think this number I pulled out of the last meeting that we had last year, but I'm hoping that we can actually take away this question mark at some point. So Marcarian 1018, this lovely galaxy, is at redshift 0.04. As you can tell, it's a merger remnant. It's a bit funny looking. Hopefully that's translating to the screen in there. And it was first identified in the Marcarian survey, which was a UV bright galaxy survey in the 1960s. It was then classified as a type 2 AGN in 1979 with this spectrum. And then in 1984, it changed to a type 1, gaining broad emission in both H alpha and H beta and additional continuum emission. So this was one of, not the first, but one of the first changing look AGN identified. So after that, it was observed by SDSS and a bunch of other stuff, still type 1. And then we selected it as the type 1 AGN as part of the Close AGN reference survey, which was one of the first large programs on the VLT Muse instrument. And we got a bit of a shock when we opened the data. It didn't look how we expected. It had changed back to its type 2 state. So this is when we published that second changing look event in 2015. So for the past, decade or so, we've been trying to figure out what's going on here. We need some sort of mechanism that can dramatically reduce the brightness of this AGN, somehow reduce the amount of matter in the accretion disk, and it needs to occur on fairly short timescales because we know that first change took place over 5 years and the second change was slightly Pora constrained, but is now a bit better. So it's quite hard to disentangle what's going on here with the current data. So we had a thought last year, what if we could get a much longer time baseline? And that is where we found this fantastic resource, the digital access to a sky century at Harvard, which is a digitized catalog of photographic plates from the 19th and 20th centuries. There's more than 500,000 plates spanning from 1880 to 1990 with very good spatial resolution. Also, the astrometry is done and they have been photometrically calibrated to Gaia, but very, very much worth bearing in mind that this is not intended for extended sources. These calibrations are done on stars. So I guess the other caveat here, bearing in mind we are talking about LSST, is that this is obviously a northern project, but more and more plate catalogs are being digitized over time, and I think this is something that is going to continue. So we should bear in mind other plate catalogs that could be useful. And so this is where the work of my PhD student Thomas, who is lurking online somewhere, comes in. Pictured here with one of the dash plates of Andromeda. He went through and found all of the detections of Marcarian 1018 in the Dash archive and many other archives, but we'll perhaps revisit that at some point in the future. He went through and removed all the bad data, learning all sorts of interesting things, and did an enormous amount of calibrations. And it feels a little bit shortchanged to summarize the first 4 months of his PhD in one sentence, but he's done an enormous amount of work calibrating this, which will be detailed in the appendix of this paper that you can scan, the QR code, which we are about to update. And so what he found when he made a historic light curve using the photographic plate data is that there was a brightening event that we didn't know about already that began around 1935. So this is really cool. We have a new event in this galaxy's history, so it's no longer just a 2-time changing look, perhaps it's 3, although we don't have spectroscopy to confirm that. And so you'll be asking, have we looked at the modern sky surveys? Yes, we have. So looking at the modern data, this is what we have. This is our most up-to-date light curve with all of Thomas's best calibrations. Again, this will be detailed how this was done in the paper here once it's updated. You can see we've got, SDSS, Catalina Assassin, ZTF, all these things, and our Muse observation is just in there. And then if we combine all of this, we get this beautiful 105-ish year light curve for Marcarian 1018. Sorry, the camera in the room is shaking. I hope that everything is all right there. And so we get this fantastic light curve. And so we can now go back to the drawing board of what do we think is causing this type of variability. Now, there's a couple of things we all know about these different mechanisms that can cause AGN to change in brightness. The first being obscuration, easy peasy. We put something in front of it, dims it. This modulates the brightness, but it also reddens the spectra. So we know that this is not what's happening because we can measure the Balmer decrement of the spectra at every epoch, which is a proxy for dust. We can also have a tidal disruption event, increases the brightness, but has a fairly characteristic shape of the decline and shouldn't really take more than 5 years. We've got this kind of 120-year variability cycle, so that also seems fairly unlikely. Next, we have chaotic cold accretion, which I'll cover a little bit on the next slide, which is a method of increasing brightness in a kind of cyclical fashion. It's also self-regulating. And the final is, the most fun option, which is interesting black hole dynamics that could modulate the black hole's brightness in a periodic way. And so there's been a lot of work on this galaxy, mostly focused around those two options that I outlined briefly. So I'll just kind of recap. The idea behind chaotic cold accretion is that there are clouds orbiting around the outskirts of the accretion disk in the broadline region. They collide inelastically, which allows them to shed angular momentum, and then when they do that, they can rain down onto the accretion disk, causing spikes in accretion rate, thereby brightening the AGN. Why is this one blurry? Interesting. So it can also self-regulate. In the bright phase, these clouds get pushed further out, which reduces the likelihood of infall, which kind of shuts off the process. And then as it fades, the clouds can move closer in, and you get this kind of cyclical effect. The other fun option that has been explored in the literature is binary black holes. This is a merger remnant, so this is a fun thing to think about. Is could the tidal forces from a second black hole be disrupting the flow of matter onto the accretion disk? And since we have something that's happened more than once, could this periodic cycle be attributable to something that is orbiting? Similarly, there's also been work suggesting that a recoiling black hole could cause something like this, where you have a black hole merger that's happened, and then the resulting merged black hole has a remnant kick or an amount of energy left over from that collision, which causes it to have a recoil velocity within the center of the galaxy. And then you could have, theoretically, an accretion disk form around this recoiling black hole, which then kind of oscillates around the center of the galaxy. So there's been loads of papers about all of these different ideas, and I haven't even covered all of them. So I apologize if anyone here has done this. But so in the paper that we have put out, we kind of suggest that the most likely scenario in our minds at the moment is this chaotic cold accretion, which is where in the higher state, what's happening is the accretion disk is sufficiently bright to excite the broadline region, meaning that we get continuum emission, we get broadline emission. And then when it's dimmer, there's not sufficient radiation from the accretion disk to excite the broadline region, reducing the emission as we've observed in the spectra. So just to return to this light curve, we observe this kind of characteristic timescale of 30 years. But when we do periodic analysis, we don't actually find a very strong peak. So not really 100% certain what that means. There's also this rather unfortunate gap in the data, which it would be really helpful to know what was going on here, because, we've got this brightening event happening in the 30s. And then we've got these two spectra that were observed in the 70s and 80s, but we're not entirely certain how bright the object was at that time. And so the question you might be asking is, as Swam was telling us yesterday, we are moving in this field away from interesting single object studies into looking at changing look AGN as a population and what they can actually do for us. But I would like to kind of put forward this as a test case for, can you construct a light curve of this length for changing look AGN? The answer is yes, we have managed to do this after quite a bit of pain and strife on Tom's behalf doing the calibrations. And so my hope is that we can, instead of just having this for one object, we can start to do this for many objects. And then once we figure out what type of variability we're seeing, we can start to, you know, apply models and figure out what's driving this behavior. So this is what I'm hoping we will be doing in the future. We've now got this kind of method, we hope, pretty well understood of how to generate these very long-term light curves. So we're hoping to start generating those for known changing look AGN and also any that we happen to detect that are, you know, equatorial, so that we can look at the historical and the modern data. So just to kind of conclude, I'm hoping that over the next decade, we're able to systematically detect new changing look AGN rather than just find them by happenstance. And I'm hoping that by measuring their long-term history, we'll be able to figure out how common these things are, what is causing most of them, whether it's, you know, tidal disruption events, chaotic cold accretion, weird dynamical black hole stuff, and how all of this impacts our understanding of black hole growth. So thank you for your attention.
Hi, this is Maria. So regarding your binary scenario, say the period would be very long. So presumably you may have a chance of resolving the blood flows. Have you calculated the projected separation of the two sources? Assuming a period, I know that we don't see one.
Sorry, it's very difficult to hear in the room. Was the question something along the lines of, could we resolve a second black hole if there's one in the center?
Yes.
Perhaps in the radio. We did try and do this a while ago with VLBI, and we didn't find a second radio source in the center. So perhaps it would be interesting to look with an X-ray telescope or something like that. But yeah, I wonder if that would be possible. But I guess if in order to detect it, the second supermassive black hole would also have to be active.
Any questions? Okay, I'll let Vincent take our speaker again.
Sorry, I think there's a question online.
Yeah. Can you hear me, Rebecca?
I can, yes.
Okay. Your historical light curve has a lot of gaps, and I'm just wondering if those are gaps in the absence of any data at all, or could some of those be upper limits? If you did force photometry on the digitized plates, maybe you could get some upper limits in some of those gaps.
Yeah, that's a really good point. And I was sort of surprised when I saw the light curves that there's so much data in the 30s and 40s when I would have thought that the world was doing other things. And comparatively so much less in like the 70s and 80s. I wonder if it's just to do with the plate repository that we're using, whether we have looked at, you know, the POS survey, a bunch of other ones. So we could probably try and fill in those gaps. It's just getting everything on a uniform calibrated scale so that you can actually make that plot of them all on the same magnitude scale is very difficult. So the benefit of Dash is that they've kind of done 50% of the work already. So I'm certain that you could fill in those gaps a little bit, particularly, you know, I think there's a DSS plate in there somewhere from the early 90s that could help. But yeah, there's surprisingly not as much data there as you would expect.
So you're saying in the Dash plates, there were no plates taken during those times, or it was just the object wasn't detected and so the data point got thrown out?
There were certainly fewer plates, but I think there may have been a couple that have been thrown out. Some of the plates are shocking quality, like you couldn't even extract like my poor student actually looked through every single one visually. So the ones that have been chucked out for good reason.
Okay, thanks.
Thank you.
Very nice talk.
Thank you. And next speaker is Chang Tang on the latest structure function analysis of Quasar. I'll give you 20 warning. So wait.
Thank you. My name is Jia Tam. I'm a JSPS fellow based at Heraklion University in Japan. Today, it's my pleasure to present my latest work on structure function analysis of quasar light on Atlas survey. And thanks for organizers for organizing this conference. So people who went to a meeting at Durham last year, they might have heard of me talking on the same topic. And today I'm going to talk about this on the new data set that we retrieved. So for people who are not familiar with the Atlas data, it's data that's meant for searching for asteroids in our solar system, and mainly based in Hawaii. They can regularly image the entire observable sky up to 4 times a night. There are 2 custom filters called orange and cyan, and the cadence for extra day cadence for orange is about 2 to 3 days, cyan is about 7 days. So the way we perform our analysis is that we select non-radial out brightest quasars with their coordinates and input into Atlas survey and retrieve their light curves. So this time we have almost 9 years, more than 9 years of data, double the sample size to more than 9,000. This gives us more than 22 billion observational pairs for structure function calculation. And the sample source is adapted from SDSS, so we have the black hole mass information. This is the exact same samples used by Zach that he's going to give his talk on Thursday. So here's a distribution of the black hole mass, luminosity, and redshift of our sample. So for people who are not familiar with the asset, so basically it's like we calculate the amplitude difference versus the time separation of two epochs on the light curve, and then we need to subtract the noise to get the true structure function. So in our current method, we determine the noise of each quasar based on their relation of the observed magnitude versus their intra-night amplitude change. And we fit the function, and then we can assign like a noise for each quasar. So then we bin the quasars according to their redshift, luminosity, and black hole mass, and then we perform bootstrapping in each bin in DT, the luminosity and black hole mass bin. And then we calculate the structure function by considering the noise of each quasar. So just a reminder of my previous results, we were able to show that there's a universal relation. So if we look at the data in the units of thermal timescale, so like on the figure on the right, you can see the relation is much more tightened. However, so we also saw amplitude suppression on the short time scale, and later we found that maybe that's due to oversubtraction of the noise. So if we correct that, and we will see a much more linear relation. However, in this new data set, we found that this kind of suppression in the short time scale reappears. And we don't think this is due to oversubtraction issue of the noise, because it's inside their side that where our noise is under-subtracted. So with this new data set, we have to fit bending power instead of the linear relation. And this is kind of similar to another group of people who work on the PSD. They also show a kind of bending power relation. So here is the function we use to fit the structure function. On the figure on the right here are 2 examples of the ring of our data. You can see that there's a clear breaks in the structure function, and we fit it with this bending power equation. So there are T break, there are gamma 1 and gamma 2. Those are the slopes at short and long time scale. And there's a factor S that's a kind of smoothing factor that controls the connection between 2 power location. Because of the noise and the cadence of our data, the source on the short time scale is probably not so reliable, but the breaks and the long time scale slopes, they are more reliable. For the smoothing factor, we fix at 0.1 here, but for reference, if we choose the smoothing factor to be 0.65, it's actually very similar to the curvature of the Durham dome world light function. But if we do that, the uncertainties for the slopes and the breaks will be much more larger than 0.1. So we fix at 0.1 for now. So then we try to study how those breaks and the slopes on a long time scale. So let's first look at the breaks. So these breaks exist for most of the groups, although there are still some groups that doesn't show obvious breaks, so I remove them. And also there are breaks that's too close to the maximum DT of the SF, and those are also removed. You can see if I show the breaks in the physical parameters like the direction, wavelength, luminosity, and black hole mass, it seems like there are some correlation. And this is kind of consistent with what Colin found in 2021. If we only look at the most massive parts of this data, that our measurements are kind of consistent. But we think that the relation is not so simple, like a linear relation between the breaking time scale and the black hole mass. So we try to perform a more complicated numerical calculation. So yeah, this is a complicated part, but basically what we did is that we based on the disk model and try to numerically calculate the disk size by like flux weighted disk size, and that's the time scale, the thermal time scale. And we found that if we normalize the time scales and black hole mass in a unit of square root of luminosity, we get a very clean relation that shows on the right. So yeah, that's the main point of this exercise. And we are able to like fit the analytical equation to the numerical calculated results. Sorry, this is a bit complicated equation, but basically this is just a bending model in 2 dimensions. And then we can fit this equation to these numerical results, and then describe the thermal time scale and the disk size. So what we can try to do here is to fit that complicated analytical equation to our data sets and see whether our results are consistent. And it seems like it is pretty consistent. Like so I now normalize the y-axis, the time scale and the black hole mass with the square root of the luminosity, and then the solid lines are the best fit to the data, and the dotted line are the best fit for numerically calculated thermal time scale, and they are pretty much consistent. However, caveat is that it seems like if I separate my data from that's from the origin and from cyan, the relation seems to be different. So that means that there's still some kind of observational effect here, but the time, the letters length of our data, like both the origin and cyan, and all the sample are uniform, like they are all in the same depth. So it's not due to the time span of the letter, but probably it's affected by the cadence, because origin and cyan, they have different cadence. So this is something we still need to work on. And next, I'm going to focus on the slopes. So you can see the slopes on the longer time scale, they are also kind of dependent on the physical parameters like wavelength, luminosity, and black hole mass. So this is quite interesting. And they are not like the random walk prediction is 0.5, but we see a function that's spreading from 0.2 to 0.5. So there's another work done by another student at Australian National University, ANU, and she's been working on the structure function for a low redshift, low luminosity AGN sample. She corrected back from the host galaxy and calculated the SF, and the black dots are her sample, and the blue dots is the sample, my sample. And in her results, she didn't find any breaks, competing breaks but she also found that their slopes are dependent on physical parameters. So if I combine my data with her data, you can see my data is on the upper right and her data is on the lower left on both these panels. You can see the relation is kind of continuous, and this is quite surprising. That my slope is measured above the restaurant DT above 100 days, and her slope is measured below 100 days. But these slopes, the change corresponds to the luminosity and black hole mass is kind of continuous. So that means that the disk, for a small disk on the low luminosity black holes, is probably having the same mechanism that behaves on the large high luminosity disk. Yes. So yeah. So we still don't know what's the actual mechanism that controls this yet. But I'd like to propose a new way to describe the structure function. Maybe so because the in Fourier transform it can be additive, so we can have a de random walk like that's the blue curve there, and plus the power law, and then the green line, and then that can become the bending power law of the red structure function, and they can describe our data. And then the noise is probably contributing the de random walk, and there's another physical process that's controlling the power law. However, this equation maybe is clean in structure function, but it's very difficult to convert it to PSD. Like there's no universal transformation between these two. So we tend to work it out maybe via numerical Fourier transform. So before closing my talk, I have to briefly mention another project I tried to launch recently in Subaru PFS team. So Subaru is an 8-meter class telescope based in Hawaii. There's a new instrument called prime focus scan, Supreme Cam, and then they have a survey trying to. There is an observation plan trying to observe almost 40,000 AGN candidates, and then I think this sample is very useful to study their variability with using LSST data. But we have to think that the overlap region, because one in northern hemisphere, one in southern hemisphere. Yeah, so I think that's my summary, and I'll leave it there and take questions. Thanks for listening.
Questions?
I was wondering, why do we need then that triangle? Can't we just change the model? Because your fits show that you need a more generical function. Why are we trying to keep the triangle inside?
Yeah, it's a great question. Maybe we don't need it, but yes, somehow just if I play with the equation with the bending power law and it seems like it's possible solution. But yeah, of course we can get rid of the general.
I have a very short one regarding the last slide you showed. What is the overlap of LSST with Subaru?
I don't know yet. Sorry, they're Penn. They tend to finish these observations in 5 years, but it seems that they started their observations from last year, but it seems that there are still many things many problems they need to solve. Especially, yeah, there should be some kind of graph internally somewhere I didn't know, but yeah, there should be some of that.
And we have one online. Well, Keith.
Hi. You mentioned that you excluded objects where the break timescale was too close to the duration of the observations. And I wonder if that cut was made for timescales that were only 1/10 of the total duration. Because I think to measure the break and the slopes accurately, you need a light curve that's about 10 times longer than the break. So was your cut strong enough to exclude the possibility that the low luminosity objects, you're measuring it well, and so your high frequency slope is close to zero, and the lower and the higher luminosity objects where the break time scale will be longer, you're still picking up the slope of a half that you get from the random walk?
Yeah, so that's a great question. So we have a sample redshift spreading from 0.5 to 2.4, and our observed brands our red spread time span maximum is like 3 point something, but in high redshift it's probably 2.6 something. But the cut was made like the breaks is short. The comparing the breaks and the maximum time span on the structure function, if it's shorter, smaller than 0.7 DAX, then those are discarded. But yeah, like 1 DAX is probably more robust to like the 10 times difference. Yes, I know that.
Okay, thank you.
Thank you.
Thank our speaker again. Next, about the Eddie. It was about here's that's one of the new sample of lasers. Warning, wait.
Moving more.
Don't look.
Okay, thank you very much.
Okay, let me just. Slide share. Okay, you can open your eyes.
I have no idea. What's there's like what does the X do down by the play button and the portal? Down towards the bottom of the slide, can you see it? Yeah, what are those two?
Okay, let me try just put it on. No switch. Maybe there was something. Move now.
Does it move when you try?
I don't know.
Or maybe
Now it does. Right, so. Okay.
So I'm going to present a work that was part of the PhD thesis of my students today. But before
Click on it.
okay, but before, let me briefly introduce the lasers, which are a peculiar class of AGN with one jet pointing towards us. And because of this, the jet emission undergoes Doppler beaming, which can be quantified by the Doppler factor delta, which depends on the velocity of the plasma inside the jet and on the viewing angle. The better is the jet aligned with the line of sight, the stronger is the Doppler beaming. Among the consequences of the Doppler beaming, we have that the flux that we measure is relativistically enhanced by a factor which is some power of the delta factor. And then the emitted frequencies get blue shifted, and the variability timescales get shortened by factor delta. This is why lasers are known to be bright objects and very variable. Because of the Doppler binning, the jet emission prevails. And if you look at laser spectral emission, you have this typical double bump shape where the position of the two bumps can vary according to the type of object, but in any case, the low energy bump is due to synchrotron radiation, while the high energy bump is due to inverse Compton scattering with a possible contribution of hadronic processes. We have two classes of lasers. One includes the flat spectrum radio quasars, which show broad emission lines in their spectra, and whose spectral energy distribution sometimes shows even a dominant contribution from the big blue band, that is from its quasar-like core due to emission from the accretion disk and broadline region. Then we have another class of lasers that's called VLAC objects, and they, by definition, have featureless spectra, and in fact, we don't know the ratio of many of them, or if they do, they have just weak emission lines. For the closest objects in the SLED, we can distinguish the contribution from the host galaxy. So it goes without saying that it's very, very difficult to distinguish, to identify, to select lasers in the optical band, because in addition to the very variable non-thermal emissions from the jet, you can have even strong contributions from the less variable emission from the big blue band, and even a steady contribution from the host galaxy. So we really need to use also multi-wavelength data in order to select lasers. We have several laser catalogs available. This is the list, which is not complete. They contain different numbers of objects that were selected in different ways. The big zeta cat is the catalog which is usually used when you need a reference sample, because it contains mostly spectroscopically confirmed objects. So the aim of our work was to develop a procedure that can help us to identify lasers in view of the legacy survey of space and time. And of course, we were interested to see whether we could find interesting objects, possibly very variable objects at high redshift. And we used the VZCat sources as to drive us in the selection criteria. So lasers are radio emitters, and they must have a compact radio morphology. So we looked for compact objects in the VLAS survey. And in order to select compact objects, we used two parameters. One was the major axis parameter, and the other one was this compact factor, which was defined as the ratio between the total flux and the flux at the peak. If we plot our sources in a diagram containing these two parameters, we see that almost all VZCat sources, all lasers, occupy the region in the bottom left. So we cut there to have the first selection. Then, as a second step, we cross-match our sources with the Pan-STAR survey to look for the optical counterpart. We put cats in the brightness, And we removed the extended sources. Extended sources have problematic photometry, and also we are not very interested in sources that have a prominent contribution from the host galaxy. And in order to do this, we used the difference between the photometry, the PSF photometry and the chrome photometry. Some before was mentioning this. The PSF photometry works well with point sources, but fails for extended sources because it underestimates the brightness of the object, while the chrome photometry uses a flexible elliptical aperture and so measures the whole brightness of the object. So for point sources, this difference in magnitudes is 0 or very close to 0, and we put a threshold at 0.3 and discarded all the extended sources down to magnitude 20.5 because for fainter sources there is confusion, so the method isn't working anymore. Then we wanted to exploit the spectral properties, and we can see here the plot of the radio-optical spectral index of the total sample compared with the sources with cut. And we selected all sources with a radio-optical spectral index less than -0.3. Which we saw it's the same thing of asking that our sources are radio loud according to the classical definition. Then we also look at the infrared properties. So what you see here is the plot of color plot, infrared spectral index. We used the NY's catalog for this. As a function of the optical spectral index. And you see that our sources distribute into two kinds of blobs. And the beta cut blazers are found in the upper left blob. So we discarded all objects in the lower blob that are mostly low luminous FR0 contact radio galaxies. But we are left with 77,000 objects, which is quite a lot. So in order to go on, we looked for the optical variability. Pan-STARRS provides light curves in 5 filters, and to increase the sampling, we built composite light curves using average color indices. And then, in order to set a threshold for defining variable objects, we consider the median absolute deviation on 2 different stars catalogs. And you can see in the lower left plot that our threshold was set by taking for each magnitude bin the median of the map plus 3 times the standard deviation, and we applied this threshold. But we are still handling 25,000 objects, so we investigated what this big sample contains, and we realized that we still have a lot of normal radio quasars inside this. So in order to separate normal radio quasar from beamed radio quasar, which is laser, we raised the threshold of variability by considering now not stars, but radio quiet objects. So we repeated the last step, that the procedure that we did to establish variability, to establish a threshold for blazer-like variability. And now we are left with 3,500 blazer candidates a sample that we call result. And we saw that almost 2,000 of them are not in previous laser catalogs. They may be new blazers, and they are mostly faint sources. So hopefully, this sample includes high redshift objects, very valuable high redshift objects. So we are looking to repeat this procedure, maybe improving it in view of the latest survey of space and time. Thank you.
Just, thank you, President. Just one question. Did you use a catalog by the yacht Gordon for the VLAS?
Yeah. It was DR1.
Yeah, yes. So I strongly encourage if your group to go to the VLAS. Now it's 4 different epochs are complete now. So you could actually easily check whether that the radio flux itself has a very 4 different epochs, which separated by 2 to 3 years apart.
Yeah. We have this in our list of things in progress.
Do you have plans to acquire sort of large-scale spectroscopy for those objects, or have you checked to see how many of those already have spectra in archival data and so on?
Yes. We found about 1/3 of sources had spectra in Inflow on Digital Sky Survey. And we had a first look at them, and we have, seems that we have, say, 5% contaminants still. There are few extended objects, but maybe they are blazers with some left galaxy contribution. We have, of the remaining sources, we have about 2/3 objects which look like black spectrum radio quasars, and 1/3 that look like VLAC objects. But we have still to go on with validation.
How many more spectra do you need to complete the 1,000? How many more spectra are required to sort of complete spectral coverage of the 1,987? I mean, you could consider putting them into Sloan programs or Foremost programs to acquire large-scale spectroscopy.
Yeah, it was very nice. Yeah.
Dumb question. Can you have radio spectral index information? So see if it's flat.
Yes, I didn't mention because I was running out of time, but yes, in principle, the definition of laser is flat radio spectrum, but they are variable. So if you have to combine data in two different bands so close, you introduce a bias. This is why we prefer to go for radio optical spectra instead of radio spectra. This is
inside the VLA. Is there enough bandwidth?
No.
2 to 4 is done. Okay. Thanks.
Okay, so let's say the speakers of the field. And we're back at 15. Oh, the break should be downstairs. So. Okay. Hello.
Sorry, I'm here.
Can we start? Hello. Okay. So welcome back. In this section, we have our first speaker, Ginny Yang, who is going to talk about the topic on probing early supermassive black holes using LSST and Durham.
Hi, everyone. I'm Ginny Yang from the University of Michigan. I'm working on high-redshift quasar agents, so which means early supermassive black holes. And today I will talk about what we can do with LSST. When we have LSST and Durham, we can do it regarding the study of early supermassive black holes. So what I show here is actually image and the rhythm spectrum from GMST. So I hope next year what we can use that would be image from LSST and the spectrum from Roman. And so it's actually just like shown here, so I talk just from GMST to LSST. Okay. First, a few brief information about why we all care about the early supermassive black holes. I think we do not need to go through details, but overall, just when we talk about early supermassive black holes, high-redshift quasars, we can see that we can have constraints from different scales, and from the black hole seed black hole model, black hole growth, to the larger scale like black hole pulse interaction, black hole coevolution, and even larger scale, we can get information type constraint on large scale, early large scale formation and the cosmic realization information. So that is why we care about early supermassive black hole and early quasars. Okay, and what I'll talk about today is that topic will focus on supermassive black hole growth and the black hole host coevolution across cosmic time. What we can see is actually can be mainly described as this figure. It just this is what we can observe today. So in present day, we know there's a tight relationship between black hole mass and galaxy. So different galaxy properties. There's a famous sigma relation. But the thing we don't know is we don't know how we can have this relationship and from which redshift we can expect this relationship. It's kind of history of this black hole host coevolution due to our limited knowledge of early universe, and we don't know how the black hole, supermassive black hole grows to what we can observe the really high redshift, like Penn and supermassive black hole, right? And how the massive galaxy get built out, and how black hole hosts co-evolve together, whether they're just follow this three different models follow this line that co-evolve over the time together, or anyone can grow up first with another one catching up later. Okay. So what we can have with GMST in the GMST Europe, the first we can confirm the existence of this billion solar masses black hole by H beta emission line. Actually, the first time for high-redshift quasar with GMST, we have covered its with an optical line, and we confirm the existence of billion solar mass black hole. And again, we can see it's challenging of massive C black hole model Even a very early redshift, like redshift 30 or 20, we get massive C black hole here. And then we need high accretion rate history. So it's like overall, so over time, it's actually adequate ratios is a very early stage. Then, so that we can observe this billion solar masses black hole redshift 6.5, redshift 7.5. At the same time, the JWST for the first time can direct image restaurant UV optical stellar emission from host galaxies. So for JWST, it is compatible. And now we get diverse host galaxy from this Heraklion luminous quasar and quasar, also Heraklion Brandt AGN red dot. And now we can talk about black hole host relation and Heraklion. It's actually some recent JWST result in the past 3 years. We get all the measurements of black hole mass and stellar mass from JWST for luminous Heraklion quasars, quasars, and also Brandt AGNs. Overall, we can see it's actually they're actually most of them actually above the line. This is the low correlation right between most of them. First conclusion is most of them over massive black holes. And with UV dense quasars actually more closer to the low correlation with lighter scatter. However, it's actually quite unclear. The conclusion is quite unclear. And at the same time, we can get the we see strong interaction between black hole host galaxy, like the black hole feedback outflow up to redshift 7.5, and extremely strong oxygen-3 outflow signature from redshift 6.5 quasars. So this kind of thing tells us this is just a stage we can look at the black hole host interaction. We can study the build-up of this kind of black hole host relationship. And now the question is, so whether there is a black hole host relation at redshift 6, and when the black hole host relation appear at first time, and how this black hole host system actually settled down. If some of them just on the way settling, then how them settle down. So to answer these questions, this is what we can get from JWST equations. And to answer this question, we need another sample. We need to overcome selection bias. We need to go down to the center end to lower mass. And JWST is powerful in follow-up, but it's not a survey telescope. So that is why we want LSST and Roman theory. So what we can do when we have LSST and Roman. So here we talk about targets. What kind of target we can have. And these are 3 different categories. The first 2, they're one I will talk about today. The third one is actually when we select the first 2, sometimes we always get the third one, but I will not cover that. We don't have time to cover that. But if anyone is interested in working on that, so I'm very happy to discuss details. But the first 2, redshift 7 quasars and above. And the second one, this is not redshift, but this one will provide us valuable information about early supermassive black holes. So I'll talk about that later. And the first one, redshift 7 quasars. A few background information, but we know it's very challenging to search for these redshift quasars. So in past decades, the past 20 years, we actually this first 2 slides, this figures show there's 2 reasons why it's challenging. First one, extremely low density of redshift quasars. We see rapid decline toward redshift. At the same time, we get very, very high contaminance rates. It can be a few hundred thousand times higher number density from MMT dwarfs and red galaxies. This is our target here. As a result, so this is what we can have for JWST. So it's a sample we have is actually our story started from 10 years ago, and now we have a sample of redshift luminous quasars up to redshift 7.6, and the highest redshift quasar we know. And then it's actually probably in the next few weeks you're going to see the paper. So a large sample of Euclid quasars counting more than double the number of redshift redshift quasars and redshift, for example, of 7. And this is what we have with Euclid. And now if we have LSST and Roman, we call it LSST Euclid Roman era. So the game will be changed. We see this series is quite different. Survey areas, different depths. And this one is ongoing, and we will have LSST and Roman very soon. So we can see they cover different wavelengths, and LSST can play the key role because it is the only one with deep optical, wide field optical imaging. So here, it's about 2.5 magnitude deeper than Euclid's optical band. And Roman's much deeper near infrared. So with this kind of wide survey optical near infrared image data, what we can do is kind of prediction about how many redshift quasars and how we can change the sample size of redshift quasars. So this dashed line is what we have. It's our survey limit now. And what we can have with Rubin, Euclid, Roman, so we can reach like 3 to 4 magnitude deeper, and for redshift 6, 7, 8 to 9. Okay, essentially, if we reach redshift 9 or 10, it's really the first quasar defender and the really early phase of the supermassive black hole growth. And we can see the number we can increase the number of the known quasars about more than 1 order of magnitude. And here's one. It's just like why we want to combine LSST and Roman. So LSST provides us very extremely optical imaging. Univ we can have Roman imaging data, but at the same time we want to use spectroscopic follow-up. Spectroscopic follow-up with band quasar is always a question, but we can have some spectral coverage bright end is actually from Roman gradient survey directly. This is a simulation of redshift 8 quasar. So what we can have from the first 2 years from Roman, we can, if there's a bright redshift 8 quasar, we can directly get its 2D gradient spectrum here, and we can capture their broad emission lines are not available. So this is what we can have for high redshift quasars from LSST and Roman. So the next few minutes, I will talk about why we will care about redshift 1 to 2 later right now. It's not, but obviously it's not very high redshift, right? But it's actually very interesting and a tight constraint of early supermassive black hole growth. So the background about later down, a little bit information, just studied like more than 3 years ago. We studied this from JBC near-camp imaging data. We see all this little red dot here, just literally based on the image. And then the spectral broad emission line and V shift. So we just stop and show 5 different features from known agents. And we list over different features here like V shift continuum, no detection other wavelengths. Where high fraction of broad Barnum absorption is like 10 to 20% is much higher than what we have from lower redshift agent. So lower redshift the point something is 0.1 to 1%, and now we have 20%. And only a few, like as I remember today, is only 2 or 3 have like long-term variability. Okay, and quite a few models posted by different groups, including models with supermassive black holes surrounding the wide dense gas envelope over. So there's a high chance. So it's actually there's a supermassive black hole in the central part. However, there's also some models without a supermassive black hole can also explain these observations of later dots. And studies, if we look at black hole Hosen relation, studies of a sample of Brandt AGN with later dot and non-later dot, they actually just complete different behaviors in this black hole Hosen relationship. However, it's just a very small sample, and we actually need a larger sample. To answer these questions, whether there's a supermassive black hole center, we need to confirm that first. And we also want to know whether the later dot represents a very unique early phase of supermassive black holes, just like only existing at high redshift. And the third one is whether they have the same structure as AGNs, normal AGNs we know. So to answer these questions, what we need is a large uniformly selected sample. This actually only LSST can do that. Okay, and what we can do is LSST plus Roman. We have STB, it's actually from LSST plus Roman. We can have spectral directly from Roman so that we can have a broad line AGN survey. Just searching for these broad line AGNs by HR published in the lines. Then we can select a bit right out from XCD, so we can cover redshift 0.5 to 2.5. And then for longer term, we can talk about variability information from LSST actually to confirm supermassive black hole and to investigate the structure. This is one example of redshift 1 of V shift with right dots. We have LSST from LSST U band to Roman J band to cover emission 1 up to HR. As kind of prediction, so we actually don't know how many different we can have in the first 2 years. It's just based on quite uncertain number density prediction from what we know from Heraklion, from redshift above 2 is actually we cannot predict exactly how many, a few hundred to a few thousand right now. But this is just what we want to know to understand the redshift evolution. So whether this kind of things only exist at Heraklion, or we can expect similar redshift evolution as AGNs we know before. Okay, so kind of as a result, then we can get this variability, confirm supermassive black hole and structure, and we can use number density to understand redshift evolution, so whether this kind of early supermassive black hole only phase. Okay, I think that's the summary. Just 2 kind of targets the goals we actually want to better understand early supermassive black holes. Thank you.
Questions?
I guess I'm not familiar. What kind of variability are you looking for optical and little red dots?
You mean little red dots?
Yeah, can you already like search for those?
It's quite unclear. I mean, we don't know which kind of variability we can have. As I remember, it's just like a few months ago, probably the first one got like long-term variability detected, and a few weeks ago, the second one got always long-term variability. So we actually don't know which kind of variability you will have from little red dots. Most of the little red dots, so far, most of them we don't see variability. But I think it's also due to lack of enough multi-epoch observation of this little red dot.
What is the best cadence you can get when the Roman is fully operating in terms of studying the variability?
Oh, you mean the Roman part?
Yeah.
It's actually, Roman is not, I mean, the first 2 years is not that, I mean, it's not sufficient for the variability detection, actually. For Roman, in the first 2 years, we were used at least actually the median tail prism spectral and the imaging. There's only a small field that we may get multiple observations in the first 2 years. Yeah.
So after 2 years.
After 2 years, time domain field, we can definitely get information, but this is also a small field. So I think for the variability part, LSST will contribute.
Thank you for the presentation. I want to know what you want to select the little red dots uniform and for my AGN uniform, and what do you want to get from the uniform samples, the black hole ones?
You mean the how to define uniform, or?
I mean, what do you want to do with the uniform sample?
It's actually just so current selection of little red. For example, there's a very recent paper about little red dot, local little red dot selection using DESI-DR1. DR1 data, they actually applied color cuts to over DR1 spectroscopy observed object. However, you know, DESI-DR1 is actually pre-selected by DESI-30 selection. So what we want to do is actually know any pre-selection based on Roman prism emission line first. So we call it the Rubin AGN survey. And then we get our emission line first, and then we can apply color card to select V-shaped data. So this actually just started from Rubin. Yeah. At the same time, this is actually the spectral covered object. At the same time, we can also do imaging selected, just select it from ICD. But that will have question just for center end object, we need to do spectral follow-up.
Thank you. Okay, thank you, speaker. So next speaker we have Lankesh Vade, who is going to talk about the question: can multi-messenger data unblock the strong supermassive black hole binary detections?
Okay, thank you. Good morning, everyone. I'm Lankesh Vade, or Loki Day, and I'm a postdoc at Perth, working with Maria. And my primary research interest is detection of supermassive black hole binaries. So we all know that galaxy mergers can produce close subparsec separations from black hole binaries, and we should be able to detect them using electromagnetic observations of AGNs. Okay, because an AGN hosting a supermassive black hole binary should exhibit periodic or quasi-periodic variations in its light curve, and the periodic variation can arise due to different mechanisms. For example, Doppler boosting of the emission from the black holes due to the binary motion, binary-induced periodic accretion, theoretical self-balancing, and so on. I think we have already heard about this, and we will hear more. And based on these expectations, already many supermassive black hole binary candidates has been proposed, but so far none of them has been confirmed to be a binary. But fortunately, this EM observation is not the only way to detect supermassive black hole binaries, okay? Because the supermassive black hole binaries can also be probed using gravitational waves. And here is the whole spectrum of the gravitational waves. The x-axis is the gravitational frequency, and y-axis is the gravitational amplitude. As you can see, different gravitational experiments are sensitive for different frequencies. For example, LIGO is sensitive for like tens of hertz to 1000 hertz. The future LISA will be sensitive to millihertz gravitational waves, and pulsar timing array experiments such as nanograv is sensitive to detect low frequency nanohertz gravitational waves. Okay, but now in this spectrum, where does supermassive black hole binary falls? Okay, and if you do a very simple calculation, you can see for typical subparsec separation supermassive black hole binaries, the emitted gravitational wave has frequencies around nanohertz. Okay, so with this range, so we can use pulsar timing arrays to detect gravitational waves from supermassive black hole binaries. So we can use pulsar timing arrays to detect supermassive black hole binaries. Okay, and as many of you are not very familiar, may not be very familiar with PTS, so I will try to give a very brief introduction to PTS, how it works. As the name suggests, pulsar timing arrays uses pulsars. Pulsars are highly magnetized, rapidly rotating neutron stars. For example, this orange ball here, which emits beam of radiation along their magnetic axis. And every time the pulsar rotates, if the geometry is correct, the beam of this emission will sweep across our line of sight, and every time it rotates, we'll see a pulse like this. Okay, so pulsars are like cosmic lighthouse, and pulsars, especially the millisecond pulsars, are very stable rotator. Their rotation period is very stable. Now, very is like very because like how that is important for us, and but for our purpose, we can like think it is very stable. So based on that, we can actually very accurately predict when a particular pulse will arrive at our telescope. Okay, and the arrival time of a pulse is called TOA, or time of arrival, UA for short. Now, if there are gravitational waves, okay, then the gravitational waves can change the arrival time of pulses from the predicted values. But again, the gravitational waves are not the only thing. There are other things. For example, pulsar intrinsic noise, the interstellar medium through which the pulses is propagating, and like instrumental noise, everything also can affect this arrival time of pulses. But how gravitational will affect the pulses? In this example, you can see if there is no gravitational waves and no other things, then this is how the pulses will arrive. Okay, like this is nice pulses, equidistant in time. But if there is a gravitational waves passing between the pulsar and the Earth, sometimes the pulses will be squeezed together and the pulse will arrive earlier than expected, and sometimes the pulses will be stretched out, so the pulse will arrive later than expected. Okay, and the difference between this actual time of arrival of pulse and the predicted time of arrival based on a model is called the timing residual. Okay, and our goal is to detect the gravitational waves. Okay, now you should ask, okay, if there are other things which also affects the arrival time of pulses, how do we know whether the timing residual we're detecting is from gravitational waves or from some of those other things? Okay, and the answer is the timing residuals that is induced by gravitational waves are correlated in a certain way between different pulsars. Okay, but the other things that are affecting the TOAs, for example, intrinsic noise, the interstellar medium, and instrumental noise, they should not be correlated between different pulsars. Okay, so this correlation is the smoking gun signature of gravitational detection. For example, if there is a gravitational background, okay, then the gravitational background will induce that now special correlation between different pulsars. Now this is like a jargon for you. So what is Lynch and Downs correlation? I think with this video will be very clear. So if we have this many, here is the Earth and there are like many pulsars, and if we take any two pulsars and calculate the correlation between the timing residual between two pulsars, without gravitational waves, there should not be any correlation. Okay, the average correlation will be 0. But if the residual is due to gravitational waves, and then if we calculate the correlation, you see as a function of the pulsar sky separation, we find a particular kind of correlation. Okay, it is like positive at low angular separation and goes negative around 90 degree and again goes positive. And this particular correlation is called Lynch and Downs correlation. Okay, so because like if the residual is coming from background, we should expect a Lynch and Downs special correlation between the timing residuals of different pulsars. And we have actually found this correlation in the nanograph 15-year data set. Okay, and also many other pulsar timing array collaborations have also found very similar correlation. What we have found again, this is x-axis is the angular separation between pulsars, y-axis is the correlation, and this deep blue dashed line is the predicted Billingson-Downs correlation that we would have expected, and this point with error bar is what we have found in the nanograph 15-year data set. Yes, like the error bars are large for the time being, but still you can feel like it is following this trend very nicely. Okay, now we have found this background, but what is the source of this background? Okay, and the detection significance of this correlation is as of now 3 to 4 sigma, but as we have more and more data, this should increase with time. Now, what is the source of this background? Okay, that we have detected, and a population of supermassive black hole binaries emitting gravitational waves and get incoherent superposition of those gravitational waves is expected to be the most promising source of this gravitational wave background. Okay. Now, if a population of supermassive black hole binaries is indeed the source of this background, then we should be able to detect the loudest supermassive black hole binaries individually. Okay, and this figure actually shows that nicely. Again, the x-axis is the gravitational frequency, y-axis is the strain, and each red circles is individual supermassive black hole binaries contribute black curve, and on an isotropic background, it should be like a straight line. But as you can see, there will be some black hole contribution, like for this red big circle, which should peak above the background, and we should be detect those. We should be able to resolve those binaries from those background. Okay, and in this figure, what you can see is the parameter space of supermassive black hole binaries that can be detected through LSST or the pulsar timing array. Okay, in x-axis is the period, y-axis is the total mass, and as you can see, this light blue region is kind of the supermassive black hole binaries that will be able to detect with LSST, and this deep purple region is what we'll be able to detect with pulsar timing arrays at different times. So, if you look at the bottom line, this is what we'll be able to detect by 2034 using SK. So you can see there is like substantial overlap of supermassive black hole binaries that should be detectable by both LSST and pulsar timing arrays. Okay, and if we can detect same supermassive black hole binaries using both EM waves and gravitational waves, then we can also inaugurate the field of multi-messenger nanometer gravitational astronomy. And as you know, when we have multi-messenger observation of some object, it creates a new field, and we have lots of new insights. Okay, now not only we can detect them in individual data sets, in principle, we can combine the EM observation of a supermassive black hole binary candidate with PK data, and that can improve the constraint on the binary parameter. And this is what Maria and her collaborators shown in 2026. Again, in this corner plot, there are different binary parameters like total mass, mass ratio, frequency of the gravitational wave, and this is inclination angle. And if you see different curves, for example, let's look at the mass. Okay, the orange curve here is the constant on the mass only from the gravitational wave data or PK data, and this green line is what is the constant mass only from the EM data. When we combine both of them together using multi-messenger data, this purple is the distribution of the mass. Okay, so as you can see here, this is true for all other parameters. When we combine EM and PK data, we get much better constraint on the binary parameters. But this study assumed very idealized EM observation, like there is no intrinsic AGN variability, uniform cadence, like no seasonal gap, and also this didn't explore. Although this explored like how the parameter space will be better, it didn't explore how it will improve the detection significance. Okay, and that is the question we're trying to answer. It's like, how does the detection significance and parameter estimation improve for very realistic LSST like EM observations of AGN? Okay, to do that, we first simulated very realistic LSST like EM light curves for supermassive black hole binary candidates, and we have used Rubin sync for that. And we have included intrinsic variable AGN using the damped random walk. And for the binary signal, we have assumed Doppler boosting emission from the secondary black hole, the same signal as Sebastian has shown in his talk yesterday. And for the Doppler boosting method, it's like the secondary flux is multiplied by Doppler boosting factor, but the Doppler boosting factor is given by this expression. where omega is the angular orbital period, pi is some initial phase of the orbit, and m is the total mass, r is the inclination angle, q is the mass ratio. And in this expression, you can see like this whole term, like all those things are not individually detectable because they are highly covariant. So we combine them and we tell them, we call them this amplitude of the Doppler boosting factor. So all the model parameters become like the amplitude of the signal, the Doppler boosting signal, the orbital period of the binary, initial phase, and for the damn nova, we have this the amplitude of the damn nova and time scale of the damn nova. Okay. Now this is an example the electromagnetic analysis, and this is one of the LSST how the LSST lighter will look like for this kind of parameters. This is total mass ratio, and we used a nested sampler to detect this binary along with the damn nova parameters. And what you can see here is the corner plot of the different parameters. As you can see, using this nested sampler, we're able to retrieve the injected. So these blue histograms are the recovered posterior distributions, and the black lines are shows the injected values. Okay, as you can see, we recovered those injected parameters very well, but the base factor of the detection of the binary signal is around 20.2 with this for this kind of a light curve. Now, next, what we did, we simulated a very realistic PTA data, which goes up to like year 2034. And then injected the gravitational wave signal from the same binary okay, using the same binary parameters. And then we try to detect the binary just using PTA data from the gravitational waves. And it turns out with that kind of binary parameters, the SNR for the gravitational signal turns out to be around 4.58, which is not very high. And this is what the posterior distribution of the binary parameter looks like just for the PTA analysis. Okay, again, this is inclination, this is total mass, this is frequency. So base factor is like only 1.39. So this is like the gravitational signal from this binary is barely detectable in the PTA data set if we only use the gravitational waves. Okay. But now what happens if we combine the EM observations and the PTA data to find the small binary? Okay. And again, this is the posterior distribution. If you combine EM data and small binaries in PTA data, then you can see like all the parameters are very well constrained, along with the damn nova parameter. So this is log sigma and this is log tau, and these are like different binary parameters. Okay, these are much better constrained compared to both only EM only observation and also PT only observations, and it gives a significantly stronger detection of the binary. Okay, and yeah, as I said, binary parameters are also like better constrained as expected. But if we calculate the base factor, and for this kind of analysis, we use Savage-Dickey base factor, and the Savage-Dickey base factor turns out to be infinity because for very strong detection, the Savage-Dickey base factor doesn't work very well. Okay, but still it suggests the detection significance is very high. Okay, so as this shows that combining EM and PTA data improves the detection significance even when we have very realistic LSST like data set. So what next? Of course, explore alternative detection significance for strong supersymmetric detections because Savage-Dickey base factor doesn't work well. Explore the full supersymmetric binary parameter space. Here I have only shown one example. In fact, what I have been seeing is for kind of binaries which are like well detected by PTAs, most of the binaries, the magnitude of the AGN is above the saturation limit of LSST. Okay, so you also need to think about that. Also quantify how PTA data can help rule out false supersymmetric binary candidates just from EM observations, and incorporate additional binary signatures. For example, like this is only for circular binaries. What happens if we have eccentric binaries and other binary model like self-cleansing, and of course finally apply this to real data sets. Okay. And that will be all. Thank you for your attention.
Thank you, Locke. We have time for one question.
Thanks. So, did I hear you right again when you said that most of your candidates are going to be above the LSST saturation limit?
Many of them, because in PTA, like what we see, the closer the binary and more massive the binary, it is better for us to detect it with PTA. Okay.
So those sources should be existing candidates from Atlas or ZTF or shallower surveys.
Yes, but that's what it's like. Again, I'm using green light to calculate what will be the magnitude, and many of them turns out to be like more than 60. I'm assuming 16 is the like saturation limit. Again, this is like preliminary. I will like do this in more detail. This is like very much one ongoing project. So other surveys will help, but just from LSST point of view, it may not be like very good for those very strong PTA quantities.
Okay, let's thank the speaker again, and we'll begin the meeting.
Of the European culture, also, of course, together with the Italian culture. But here is the cradle of the democracy and all of these services, and it is great honor to be here, of course, with all of you, experts from various disciplines united together under the banner of the LSST and the AGN science collaboration. On top of this, it is also like in the home because our queen, Catherine, is the Greek princess. So, yes. So thank you so much. This is not the in-kind update. We are the LSST CERSAG in-kind team, and we are not updating on the in-kind contribution. However, here is actually quick update on the recent development regarding the publication of the Quasar Harmonic Explorer hub paper that was actually submitted together with all wonderful colleagues that you can see here, and apologies for making the order of the names. The order doesn't mean importance, that is also just representing incapabilities of our human language that I can put all people on the first place. So this is just quick report on what you already be shared with all people. Some of contributors are here on the reviewer responses, and we can open discussion on this, but also we would like to outline some possible to say possible routes for the analysis of the data. As we already heard a wonderful talk by Loki Day on importance of the cross observational analysis of the signals regarding the binaries, and I would like to add to all other signals. So with the multi-messenger data and multi-band of the LSST, we need actually to analyze the cross observational to say surface. So it is not enough to have the signal in one band, but actually it should be somehow propagating through all of, to say, bands, and some analogy will be maybe with helio seismology. And here you can see a wonderful example on the blazars, Yanis, Claudia, and other people from that community. You can see how much actually we have the repetition of the information after maybe several years, that periodic signal in phase can reappear once again, and it can be maybe explained like switching off the jet. And also you can see how much of the nice information can be seen in the millimeter and radio data. So we need radio people and also X-ray people and also millimeter people. And we get nice talk from Professor Adam Hinks from University of Toronto last week, presenting the ACT telescope data, and you can see how much actually in the optical we have the rotation of information. Regarding QAJAX, regarding QAJAX, you know about that pipeline. It is actually cross correlation of the wavelet transform. And whenever we are going into higher dimension by transforming the light curves, it means more computational power to be much more slower. And also we are applying the statistical vetting on the possible aliasing within the cadence of the LSST, and also we are applying the geometric crossband coherence, where we are actually treating the detection of the periodicity or oscillatory signal, whatever, as the actual probability region, and we enforce convergence of bubbles level on the 99%. And actually includes the cross-matched AGNs with various external catalogs, and from about 1,500 quasars, we actually, through our pipeline, that is the hub, I'm sorry, it is so, that is the hub, also we actually detected the one interesting candidate. The hub itself can have various pairs of the and distinct interactive capabilities. And here is, for example, of those 1,500 objects, we sift about 428, and you can see how much actually the distribution of the features of the light curves are skewed, and you can see how much the cadence is highly variable. And what is important is actually that our candidate is lying in the highest mode of the mean variance. It is not in the tail. We are not sampling the tail of the distribution, and something similar with von Neumann ratio. So this is the needle in the haystack of 1,400 objects. What we can see that the oscillation is isochronous. It is actually appearing in all bands, but the phase is non-synchronous. So it means that the period of 2.7 days are not originating from the G or any of these bands, because we will expect about 15 to 50 days of the periods. So it means that something is sticking outside of this. And in our catalog, you will find all these images for about 428 objects alongside the fits features and alongside our preliminary statistical analysis of the possible fitted sinusoids. On the left side, you can see how when we fit the sinusoid, pure sinusoid, and you can see some kind of the trend in the first subplot, and that is something interesting for us. And when we take a look into James W. archival data, our colleague Uroš Meštrić unearthed this nice image, and when we show this image to the people from our Illustris simulation team from the Astronomical Observatory, they thought, oh, we can see a bunch of such objects in our simulations. It looks like the minor merger, 150 to 1 ratio of the masses. You can see wonderful tidal breach. It is maybe first, second, pericenter passage. Why? Because the tidal bridge is really nice. And what is interesting here is actually that we do not know the discrepancy in the redshift might indicate that the velocity in the passage is about 1,500 kilometers. That is 2-3 times higher than what is observed in the simulation. So we are applying for the possible spectroscopical follow-up in order to determine exactly the object 2 redshift. And this is interesting because the tidal bridge can inwardly affect the object line and then make the instability in the accretion disk. How? By maybe rising the accretion rate. So the distance is between about 6.6 up to 7 kiloparsec between them. And as I said in the previous, we noticed some slight upward trend. And it was actually, we tried to remove linear trend and then quadratic parabolic trend. And you can see how it looks like the phases fitted, after such the trending. And also, here on the right side, you can see how it looks like when we fit the sinusoid on top of the quadratic trend. Why quadratic trend? Because 32 days baseline is too short, for example, for 100 or 150 days of the day trend on log time scale. But when we take into account the quadratic trend, you can see how nicely actually even Z band is aligning with this. And what we next have done is actually that we try to transfer the phase differences into time lags, and we actually inverted the thin disk model, and you can see actually that based on the sign of the phase and the level of the time lag in the G band, it looks like that G band leading what is happening around the R band, but also in others. And from this fit, we inferred the slope, giving us possible velocity of the propagation of the signal about 0.1 of the 10% of the velocity of the speed velocity, and the point zero is about 391 gravitational radius from that fitting. So it seems, because we have the plus on the right from that pivot point and on the left negative, it looks like that we have the something going in dual direction, outward and inward. And it might be because it is between in some Goldilocks zone. It can be like kind of the radiation pressure that is, or magnetohydro, some other hydrodynamics effects. We tried to recover the time lags from the inverse reverberation mapping using the methodology described in these papers. And you can see on the right, you can see on the left up the inferred transfer functions. The Z transfer function is wider. It looks like that it has some contamination from the broadline region. On the right, you can see solid black line, how we actually inferred the line curves. And on the left, we can see that actually as the disk is bluer, it is, to say, more temperature perhaps, and it maybe we have indicate that we have some temperature heating wave going through this. So this is what can happen in the disk, that we have something peaking at 84 between 84 to 150 gravitational radii, and then due to instability, high instability of the disk because of maybe tidal interaction, we have around 340 gravitational radii launching of the wave going up and inward. So that is like in the case of the stars, when we have some something oscillating inside, and then we are detecting the aging values of the oscillations at the top of the surface of the star. And and you can see the phasors of the intensity of the light curves and how they are actually moving the phases across the observational period. Thank you.
Do we have any question from early careers? Also non-early careers?
So for the very interesting source you're investigating in the deep field south, what were the underlying data sets entirely that were utilized? What were the data sets you used, to study the variability? I didn't fully follow what they were.
LSST, sorry.
Pure LSST. Okay.
LSST TP1.
Okay, fine. I mean, there are a lot of wonderful archival data in that, from Penn stars, from dark energy camera. Have you looked at some of those data?
No, not yet. That is good point. Thank you, Neil, for this, because we need, to translate somehow the light curves into one and the other, and to align them in order to analyze. But it can be done, and we can see how much actually in the first slide that optical can be really problematic, as you can see here.
Yeah.
So.
Yeah. Well, then they could give you a considerably longer time baseline, which hopefully would be helpful for you.
And we also, in the case of the ZTF light curves, if we have highly cadenced infinite, highly rhythmic infinite cadence, then it should be also carefully taken into account what point, not always body center, because we have been asking Paul about this, and also maybe if I can use this opportunity to ask Paolo, who is our actually liaison for the in-kind teams. So, is there any update regarding for the in-kind team, in order if we are coming into the maintenance phase, because we are now in the maintenance phase, deploying the code, and what is the procedure, no? For the maintenance.
So Sebastian knows a lot more, but I think the maintenance is just making sure it's available to the collaboration. Like, is there a website if I want to go download the package to make sure it's there, and then whatever updates you make, but we're done in a timely manner, and there's documentation. So, for example, I was very curious. I'd like to go and download and see what's going on, but I have to be part of the working group. But if you had some examples, the paper, for example, on a nice website, I think that's what we're looking for, to make it usable to the rest of the collaboration. And then the other thing, maybe to have a feedback mechanism page where someone can say, hey, this doesn't work.
Yeah.
So someone can fix it.
Yeah, thank you so much. We posted the paper on the AGN collaboration project, and it was approved. And also we have, that is a good point, to advertise on the AGN channels on the possibility to reach us through GitHub or.
Yeah.
Thank you. That is good. Thank you.
Okay, maybe quick question.
Yeah, I just want to add to Niel's comment that this is in the time those DST data. So I showed you some of a piece of that. We haven't done a proper analysis, but we shared with them, and we were starting to look into that, of course.
Thank you, Maurizio. That is much appreciated.
Let's all thank Angelica again. Now our next speaker is Amit Kumar Mandal, who is going to talk us about Halo in the LSST era. Once we have set up the presentation.
Good afternoon. I am Amit Kumar Mandal. I am a postdoctoral fellow at the Center for Theoretical Physics of the Polish Academy of Sciences, where I am collaborating with Professor Bojana Charni and my other collaborators from Vincent. So the title of my talk is Halo in the LSST Era, a physically motivated AGN monitoring program to measure the Hubble constant. Active galactic nuclei are among the most luminous objects in the universe, and the sizes of the different components in the central parts are mentioned here. So from these size measurements, it is clear that the central parts of AGN are very compact. Naturally, the question is, can the central regions of AGN be resolved? It is difficult to resolve these regions using any current imaging technique, but there is an indirect way to probe these regions, which is known as the reverberation mapping or echo mapping technique, where time resolution can be sought for the spatial resolution, and this method uses an intrinsic property of AGN, that is the flux variability property. Because emissions at different wavelengths are coming from the different parts of AGN, like X-ray continuum is predominantly coming from the corona, whereas the UV continuum is coming from the accretion disk. The H beta emission line and the NR continuum are coming from the PLR and the torus respectively. Now, as light takes some time to travel from one point to another point, there will be a delay between these light curves. If we can find the delay, suppose the delay is delta t, and if we multiply the delay by the speed of light speed, that will basically give you the size of those emitting regions. So this is the basic concept of reverberation mapping, and using this reverberation mapping technique, it is possible to constrain the size of the accretion disk using disk mapping or the continuum reverberation mappings. So here I am showing you different UV optical light curves for the target AGC 5548 from 1st year 2016, and as they are showing correlated flux variations, so the interval time delays are obtained, and they are plotted as a function of wavelength, which is known as a lag spectrum, which is shown in this figure. And according to the standard disk model, this interval delay should increase with wavelength following a power law, which is given by this equation. And if we fit this lag spectrum by using this equation, then from this normalization constant tau 0, we can estimate the size of the accretion disk at the reference wavelength lambda 0. So this is known as the traditional disk mapping, where we assume that the interval delays follow a power law dependency on wavelength. Now, this traditional disk mapping is applied to a number of AGNs, then the disk sizes are obtained, and in this figure, I am showing you the comparison of the disk size, observed disk size as a function of the expected value from standard disk model. And you can see that the observed disk size is about 3 to 6 times larger than the expected value. So this is known as the disk size anomalies or the larger than expected disk size problem. And another important feature is observed in the AGN lag spectrum. This is the lag spectrum of NGC 4593, and a prominent excess lag in the U band, that is around the Balmer 3646 angstrom. An excess lag is observed, and this Balmer jump is actually originating from the outer DLR region. There are also microlensing study of gravitational lens quasars revealed about 4 times larger disk sizes. Therefore, the continuum lags are contaminated by the diffuse continuum in the BLR as well as the BLR emission lines. Now the question is, what are the applications of this continuum time delays? One of the main applications, in cosmology is to infer the Hubble constant. Because you know that AGNs or quasars are not standard candle, but their properties can be used to standardize them. And the advantage of using quasars is that they span a large redshift range up to 10. So in 1999, Ulay et al. Proposed equation where the continuum time delays can be used to estimate the Hubble constant. And Capital in 2007 applied this method to NGC 5548 data, and they estimated a Hubble constant of 15 km per second per megaparsec, which is much smaller than the expected value from Heraklion model. But please note that during those times, the physical origins of the continuum time delays were not properly understood. Therefore, to study the physical origins of the continuum time delays properly, we have initiated a long-term AGN monitoring program, which is known as HALO. That is Hubble constant constants through AGN light curve observations. The primary aim of this project is to study the physical origin of interval continuum time delays, and then via simultaneous lag spectrum and ACD modeling, we will be estimating Hubble constant. So we initiated HALO program in 2024 using 60 centimeter Observatory Market telescope, which is situated in Chile. And for monitoring, photometric monitoring, we are using 4 intermediate strong band filters in UV-BY and 1 Johnson-Cousins filter in I band. And here I am showing you an example of the spectrum of Heraklion line, where the filter response curves are also overplotted. Now I am showing you an example of the light curves obtained from our HALO observations for Heraklion line, which are shown in this figure in 5 filters. And you can see that they are showing correlated flux variations. So we used interpolated cross correlation function as well as Pyroa and Javelin to find the interval delays. After getting the interval delays, then we constructed the lag spectrum of Heraklion line, which is shown in this figure. And also we integrated measurements from the suite observations which are shown by the black points. And then we fitted the data lab spectrum by using the conventional disk mapping, which is shown. This is the power law dependency, which is shown by the dashed red line. And you can see that the conventional disk mapping fails to capture the individual features present in the lab spectrum. That is the atomic features present in the lab spectrum, this gamma jump around 3646, and also an excess lag is observed in the largest wavelength, that is in the I band, which we think that this is because of the dust contamination from torus. And also this conventional disk mapping fails to capture the delays at the shortest wavelength. And we think that there is a potential contribution from the warm corona in these regions. Therefore, to characterize the interval continuum time delays properly, we are developing a physically motivated model for AGN continuum time delay fitting as well as the spectral energy distribution fitting to constraint H0. And we give the name of the code as the horizon AGN code. So in this model, first we assume lamppost model plus outer gold disk. So according to the lamppost model, point light source is producing X-ray radiation, which is known as corona, and it illuminates the accretion disk at radius r and produce flux, which is given by this equation. And because of thermal reprocessing, a Planck spectrum is produced with a temperature Tr, which is defined by this equation. And from this Planck spectrum, by using this equation, we can construct the transfer function for the accretion disk. So here I am showing you the constructed transfer function for the accretion disk for Heraklion by using the parameters which are summarized in this table. So this is the accretion disk transfer function at different wavelengths. Then we measure the time delays at different wavelengths from this accretion disk transfer function, which is shown by this dashed blue line and on the observed lag spectrum. And you can see that the inferred time delays are much smaller than the observed values. So to match with the observed values, then we are including the other reprocessing medium as well. So this is the complete picture of our model. So we are also including warm corona as well as the BLR region and the dusty torus region to construct the total transfer function. So this is the total transfer function where the first term represents the accretion disk transfer function, the second term comes from the warm corona, the third term comes from the BLR region, and the fourth term comes from the torus region. And to construct the warm corona transfer function, we are assuming a half Gaussian transfer function, which is modulated by the X-ray power law spectrum. And to construct the BLR transfer function, we are using BLR dynamical model for which we are using our own model, that is Shadow model, field relative accelerated dusty outflow model, and to construct the dust transfer function based on first approximation, we are assuming a half Gaussian transfer function. And remember that both the BLR response and the dust response will be modulated by the emissivity profile of those emitting regions. So the BLR emissivity profile is computed using cloudy, and the dust emissivity profile is computed by considering a black body spectrum with dust sublimation temperature of 1500 Kelvin. Then we combine all of these responses to construct the total transfer function. So here I am showing you the results for the lag spectral fitting for Heraklion. So in the top panel, the leftmost figure represents the accretion disk transfer function at different wavelengths. This is the warm corona transfer function, and the third figure represents the BLR transfer function from Shadow. The fourth figure represents the BLR emissivity profile from cloudy. The fifth figure represents the torus transfer function, and the sixth figure represents the dust emissivity profile. So we combine all of these responses to construct the total transfer function, which is shown in the bottom left panel, and at different wavelengths. Then we computed the delay at different wavelengths by using this equation, and then we plotted the model recovered time delays on the observed lag spectrum of Heraklion, which is shown in this figure, where the points with error bars are the observed time delays, whereas the red circular points represent the model recovered time delays. So our model successfully recovers all of the observed time delays within the error bars. And the advantage of this model is that this model is independent of luminosity distance. Therefore, we can fit simultaneously both the lag spectrum as well as the spectral energy distribution at different luminosity distances, and the best fit parameter can be obtained by using the chi-square minimization technique. So here I'm showing you the best fit spectrology distribution fitting for Heraklion line, where the black square points represents the observed AGN continuum, whereas the red solid line represents the model recovered AGN continuum, and the individual components to construct the total AGN continuum are shown in different colors. And you can see that we have successfully recovered the observed AGN continuum. And the chi-square values as a function of different lunar distances is shown in this figure. And from the chi-square minimization, we found the best lunar distance for Heraklion line is 189.9 megaparsec, which corresponds to a Hubble constant of 72.4 kilometer per second per megaparsec, with an uncertainty of about 5%. And the first application of our model was on NGC 5548 data, which is published in JASA 2025. Now, in this figure, I am showing you the comparison between the results of NGC 5548 as well as the Heraklion line, and you can see that both the targets are giving consistent results. This consistency also indicates the potential of our model to address the Hubble tension when it is applied to a large sample. That is our main motivation. And in this place, LSST can play an important role. Because currently we are suffering an uncertainty in the estimated Hubble constant of about 5 to 10% for a single target, and LSST is going to provide continuum lab measurements for about 1,000 regions in each repelling field in 6 different filters, and we have total 4 repelling fields. So therefore, we have 4,000 agents, and if we apply our model to those 4,000 agents, then that can potentially reduce the uncertainty to below 0.2%. And in this way, we can address the Hubble tension. And more details on our HALO program and its synergy will be presented by Sivagya Pandit. Thank you.
Question.
Hey, maybe when you mentioned and I missed this, can you tell a bit about the SED part of the code that you are planning? Yeah, so I mean, do you also plan to make it more broader for all sort of AGNs in general and create a SED modeling code that would also involve modeling of this time delay?
Yes, that is possible. It's possible.
So I'm getting the Hubble constant is great, but I love AGN. So for your 2 different AGN that you fit these models to, I'm assuming you have to do some pretty big knob twisting to get all these different SEDs to fit to each specific AGN. So what can you tell about the difference in like the broadline region for this NGC 5548 that you did? Like how do those broadline regions compare? Like,
okay, so we noticed that different agents are showing different percentage of DLR contamination. Like for NGC 5548, it was about 30%. But for the Heraklion, we are getting about 10% from DLR and 11% from drugs. And interestingly, in NGC 5548, we did not notice any contribution from dust. So agent it is different.
And I guess what I'm saying is, if we believe this model is true, is there any corroborating evidence that's like, oh yes, when we look at NGC 5548, we don't see any dust in its STD anyway, so that agrees with this model? Or that, yeah.
It's difficult because different agents are showing different properties. That's why now we are facing problem. So this model is quite time consuming, and previously we thought that we can do some kind of technical model, but we found that we have about 10 free parameters, and we thought that perhaps there could be some dependency and we can reduce this number of free parameters, but we are still struggling because they are different from object to object. So to reduce this different natures, so we have to study for a large sample. Then we can have an idea.
Yeah, I mean, that makes sense because AGN are all pretty different from each other. But can I ask, actually, for the Ferrel 9 case, right, there are many public light curves for Ferrel 9. Does this same model work if you look at a different epoch of Ferrel 9 observations?
Yes, like the swift of we also include swift observations.
Sure, yeah,
they are
swift
called different.
So it works for different epochs.
Yeah,
same model.
so and interestingly, they are consistent. So there is no evolution of the data.
Okay, yeah, that actually really surprises me because the lag spectrum changes a lot. Yeah, yeah, that's surprising. That's cool. I mean, that's a good piece of evidence to.
Okay, maybe in the interest of time, we can take the question that I saw popping up on Zoom while we set up the next meeting. I don't know how to visualize the chat.
I think the question was how the cadence of the LSST measure affects the H0 measurements.
Okay, and that's a very good question because from LSST we are going to have I think 5 interval delays, and yes, there may be some effect, but if we apply it for large samples, then maybe the systematic can be reduced. But yes, we have this limitation of the number of points in the lag spectrum.
Okay, let's thank Amit again. Oh, wait. I don't hear you. Wait. Okay, put it down.
Maybe it also if you can use the mouse.
This should be slideshow, right? Yes. Okay, so we have let me go. Wait. I'm moving it now. The other one should turn off. Yeah. Okay. Okay, so the next talk of the session is by Eden Davis, who's going to talk about simulating supermassive black hole binary light curves in LSST. Please.
Hi, so I'm a graduate student with Maria over at Washington State University, and I will be presenting my simulations on black hole binary light curves. So to provide some context, when we're searching for black hole binary signatures, we're usually looking for periodic emission coming from AGN. And up until now, it's been very challenging to identify these signals because we have to track these periodic signals cycle after cycle and be able to actually distinguish that from the intrinsic quasar variability. So they kind of require us to be taking high resolution observations at a high cadence and over long baselines to be able to confirm these. And previous telescopes and surveys have kind of been missing at least one of those 3 things. And then previous searches are typically just focusing on the sinusoidal binary signals, which is not necessarily representative of all of the possible signals, so they may have overlooked some of those more complex signals that deviate from the sinusoid. And as a result from that, we have no confirmed binary detections yet, but with LSST observing over 20 million quasars with this high resolution, rapid cadence, and very long baseline, we have a much higher chance of actually being able to detect these signals and have enough confidence to start getting a bigger, more confident candidate list. So our goal with these simulations is to kind of provide a very large data set with a bunch of different binary signals in order to use these as templates to start looking for binary signals in LSST data. So binary systems, as we've heard before, are formed during galaxy mergers where the 2 black holes are brought together and they'll be surrounded by a bunch of gas. And as they get closer and closer and become gravitationally bound, they exert these outward torques on the gas, and that clears out a cavity from the center here, which is kind of what you can see in the dark area there. And as the black holes start accreting from the inner region of that disk, they will suck in streams of gas that end up getting bound to each of the black holes. And those mini disks shown in blue in this picture will move with the black holes as they orbit each other, and they get very hot, and that produces electromagnetic emission, which is what we're looking for when we're looking for these periodic signals. So the first of the three signals we focus on for these simulations is first the accretion modulation signal, which just comes from the black holes accreting faster or slower at different points in their orbits. So when they're at pericenter, they're going to be accreting faster and therefore getting brighter, and then when they're going to accrete slower and get dimmer. And then the next signal we look at is the Doppler boosting effect, which happens typically just for relatively edge-on binaries. And so when the black holes are moving towards or away from us along our line of sight, we'll be seeing red shifting or blue shifting, and that gives us this brightening and dimming depending on whether they're moving towards or away from us. And then lastly, we have the gravitational self-lensing signal, which, similar to the Doppler boosting, is also prominent mostly for the edge-on binaries. And that happens when the two black holes will be aligned along our line of sight, and the black hole that passes behind the other will have its emission lens towards the observer and give us these bright flares. So we'll be seeing two different types of flares, one from each black hole. So if we have a brighter black hole and a dimmer one, we might see a brighter flare and a dimmer flare for each time they orbit. So in order to develop the simulation model, we first inject these periodic binary signals. And to do that, we use the bin-like code package, which simulates all three of those signals using the physical binary parameters like total mass, eccentricity, period, etc. And it's originally designed just for equal mass binary systems. So we have worked with some of the hydrodynamical simulations that Magnus Hewitt has produced and incorporated those into the bin-like framework so that we can model both equal mass and unequal mass systems. So the plot over here shows all three of the signals exhibited simultaneously. So you can see the sharp flares are from the self-lensing, and then the overall kind of sawtooth shape is from the Doppler boosting and the periodic modulation. To our simulations is to add the quasar noise, and for that we use Weishuang's easy tau code, and we specifically add the Diabrennan-Mark and diachromonic oscillator models, which we'll talk about more in a couple slides. And we define the inputs for those two different noise models using correlations with the binary parameters so that we're making realistic noise for the specific binary that we're submitting. And then the last step is to turn these into something that look like what LSST will be detecting. So we use Rubin sim to simulate photometric errors, which are based on the magnitude of the signal. And then we downsample our light curves to the LSST cadences based on the different sky positions that we kind of randomize. So that we'll have some observations in the wide fast deep and then some in the deep drilling fields. So our parameter space, we try to keep very broad and uninformed so that we can have, again, this diverse range of different binary signals. So we randomly select each of these parameters shown here and essentially just check whether that combination of parameters will produce something realistic for what LSST can detect. So we check if it's too dim or too bright to make sure that our final data sets are just binary signals that actually will be potentially in the LSST data set. So if the binary signal is dimmer than the limiting magnitude across all 6 bands, we reject those parameters and reselect them. And then if it's brighter than the saturation limit in all 6 bands, we reject those. And then the other 2 parameters that aren't on the table here are the Eddington fraction, which we select based on the total mass using some correlations between.
Someone is unmuted online.
Oh.
Can you please mute where you can find it though?
Press S.
So we select the Eddington fraction based on distributions between Eddington fraction and total mass from SDSS. And then for spectral slope, we determine that based on the emitted wavelength using the results from Vandenberg et al. And so with these simulations, we produce 4 different data sets, each of which will have 600,000 simulations. So the first 2 data sets will have the binary signal and the quasar noise. So we'll have a data set that has the binary signal with damper and walk noise, and then the data set that has the binary signal with damper harmonic oscillator noise. And then we'll have 2 noise-only data sets, one with damper and walk and one with damper harmonic oscillator, which we can kind of use as a null case once we start trying to test periodicity detecting algorithms. And then to ensure that we're getting equal representation of all of the different periods of signals, we separate each data set equally by 3 different period groups. So that we'll have short, medium, and long periods. And then each of those groups we separate based on what we're expecting to be the splitting between LSST's time, simulating the wide, fast, deep, and deep drilling fields. So we'll do about 90% of the simulations with the wide, fast, deep cadence, and then 10% with the deep drilling field cadence. And then each of those fields are split equally amongst 5 different signal models. The different signals are just comprised of those 3 signals I talked about before. So the Doppler boost, the self-lensing flare, and the accretion modulation. So we just combine those differently so that, again, we have this diverse range of different binary signals distributed equally amongst the different fields, different periods, etc. So here are just some example light curves. So there's each of the 6 LSST bands for a wide, fast, deep, and a deep drilling field detection. I've manually offset the light curves so that they're not all on top of each other, but they're both around 20 magnitude. And you can kind of see clearly that the DDF observation will give us much more dense observations of these light curves to hopefully sample them enough to get some more confidence in whether or not we have a binary signal. And so we are almost done simulating all of our data sets. Hopefully within the next week, we will have everything finished. So here are just some summary statistics from what we have so far. So what this is showing is the acceptance rate, which is the for each kind of combination of parameters. So the total mass, redshift, eccentricity, all of those. We compare how many of those we've accepted divided by the total number of accepted and rejected combinations of parameters. So in the yellow boxes up top where it says 100%, that means there are no combinations of parameters with that mass and redshift that resulted in the signal being too bright or too dim. There were no rejections for those cases. So the 2 main features we see here are for the higher masses and lower redshifts. A lot of those start suddenly getting rejected because they're too bright and they are above the saturation limit, so we have to reject those. And then kind of the opposite case for the low mass or high redshift cases, a lot of those are too dim, so we have to kind of throw out those parameters, reject them, and reselect over and over again. So we have kind of these 2 different regimes where we're seeing a lot of rejected parameters from the simulations. And then just to clarify, our final data set does have an equal distribution from all of the different masses so that we're not over-selecting the higher masses. And so we simulate each of the mass ranges independently so that we're kind of forcing each of those ranges to be represented equally. And then the last thing I have to show is just a color map showing the number of observations that we simulate in each different sky position. So you can see that we capture the different features of the LSST cadence. So the yellow regions are where there's more observations for the deep drilling fields. We have the galactic center in orange over there because we'll be taking more observations there. And the bluer region is the Dusty Flame mini survey where we're going to be taking less observations. So just kind of to show that we have this broad range of different cadences shown to be fully representative of the LSST cadences. So I have a quick summary here, and once we have the simulations ready, our next steps are to start training a periodicity detecting algorithm using these simulations. And the noise-only cases will work as our null case to test false positive rates to see how these algorithms are doing with just detecting single black holes and thinking that they are binary systems. Yeah, hopefully our data sets will be ready in the next week or so, and those will be made publicly available. Thank you.
Thank you very much. Kieran, do we have questions?
Thank you for the great talk. I was wondering, for the signal to be injected for the period, like what are the theoretical predictions like for ranges are you most likely to get?
I believe we are looking mostly for kind of in the middle range where we're going to capture multiple cycles so that we can confirm that we're seeing a periodic signal. But I'm not sure exactly if there's one particular specific range from there.
Like theoretically, you're as likely to get any of the weekly sets you injected with the data.
We simulate them all equally so that if there is a preference towards one, we'll have a thorough amount of simulations in each area there.
Thank you.
Maybe one more question. Do we have it? We can do two quick ones.
Yeah, just have a quick question. When you're simulating damper noise, since it has trouble at really short cadences, and some of those get downsampled to DBF cadences, do you ever use any bin averaging to avoid probing the fluid timescales?
For the damper and amok, we don't average anything, but we do simulate the damper and amok so that we have a data point every minute or so that we're able to have like a dense observation of the damper and amok to then downsample to the DBF.
Maybe, very nice. What is your perspective to see self-cleansing flare, even if it's a simulation? If you process the data and imposing it the LSST cadence, do you have an actual case you convince yourself, okay, we are seeing the self-cleansing? How often do you think you will be able to see this event?
That's a good point. It does kind of depend. You can kind of see in these cases, it depends on whether the cadence happens to line up with one of those flares are. So you can see in these, there's maybe some points throughout some of the bands that'll catch the flare, but it is kind of hopefully we're lucky enough to capture one of those flares when it's happening.
Maybe very quick question and very quick answer, and then we move on.
Yeah, I actually have an answer for that. Maria might know Kevin's work about self-cleansing flare. There's a student at East who simulated the self-cleansing flare and used mesh filter and tried to recover the parameters and see how many are detectable in LSST. Basically, for a long duration flare, like 30 days or something,
30 days.
you can recover a few thousand to maybe tens of thousands.
Okay, let's thank Eden again. And then I guess that for the last talk, I should stop the sharing. So allow the speaker to start sharing. Okay, now the speaker should be able to share the screen. So the next speaker is, and the last one of the session, is Luis Mateus Dorado Sanchez, who's going to talk us about broad double emission line quasars. You can share your slides.
Hi, can you listen me?
Yes, we are not seeing your slides at the moment.
Okay, just a second.
Yep, I think now we are about to do it. All right, perfect. I'm gonna sit in front of the camera. Do you want a 2 minutes warning or?
What?
Do you
Sorry?
want a 2 minute thing for the time of your talk or no?
Sorry, I could not understand. My audio is very bad.
I don't know which microphone is being used. This one? Okay, yeah. Okay, yeah. You can take it away. You can start. We are seeing your slide perfectly, and yeah, please.
Okay, let's move this. And okay. So, hi everyone. Thank you for your attention. I am Luiz Matheus Sanches, PhD student at Federal University of Rio Grande do Sul in Brazil. And I will present the work developed by me and Professor Thaisa Stork-Bergman, focused on the analysis of broad double-peaked emission line quasars. So let's get started. So our research aims to understand the main difference between quasars with double peak in broadline region emission lines and quasars that show only a single peak in the same emission lines. So to do this, we analyze the properties of these quasars using some catalogs and comparing the difference between the subsamples. Another goal of our research was to study the photometric variability of these objects and investigate how this variability correlates with each property of the quasars. So to do this, we used the photometric data from ZTF, and now we plan to use the LSST data as soon as we can. So our sample was drawn from Light Quasar Catalog, which is based on the SDSS spectra. As I already said, the photometric data were obtained from the ZTF, and the catalogs that we used to compare the properties were Vuenchain catalog and First Data when we use radial properties. So to build a reliable sample for our analysis, we applied some filters. So first we selected only type 1 quasars because we need to see the broadline region to select if they have double peaked or not. We have also selected only objects with good spectral quality data with signal to noise ratio greater than 20. And we choose this little redshift range here to try to reduce the bias caused by large redshift range. And in this redshift range, we can see for the most of the objects, H beta and H alpha emission line. And finally, to guarantee some reliability in variability, we used only objects with more than 100 observed nights in ZTF G-band. And after applying these filters, our sample was reduced to almost 500 quasars. So the explanation of the appearance of the double peak can be explained in different ways. However, I think that the most accepted explanation for the double peak is that the double peak originates in the innermost region of the broadline region, which depending on its inclination, it may or may not show a double peaked profile. So based on this interpretation, we classified our objects according to the shape of their emission lines. So we classified into three groups, non-double peaked, intermediate, and double peaked ones. The non-double peaked group includes objects whose the emission lines show only a single peak in H alpha and H beta, and they are associated with the inclinations between 0 and 20 degrees. The intermediate group are objects that the asymmetry starts to appear, and they correspond to inclination between 20 and 30 degrees. And double peaked group are the objects whose the emission lines are clearly showing these shoulders here, and they are associated to inclinations between 30 and 37 degrees. So basically non-double peaked quasars should be more face-on, while double peaked quasars should be more inclined. So after selecting the groups, we started comparing the physical properties between these subsamples. And we noticed that in many properties, the subsamples were separated from each other, following this trend here that you can see, non-double peaked, intermediate, and double peaked. But some of these trends were very, very strange. For example, this first one here in the mass. It does not make much sense double-peaked quasars be more massive than no double-peaked ones, since our classification suggests that they differ only by the inclination. So before I conclude something about the histograms, we try to understand in more details how each property was estimated. So in the catalog, to determine the black hole mass, they use the virial relation, which depends on this F factor here. And this F factor here, it changes depending on the inclination and the geometry, being proportional of 1 over sine square of the inclination that we can see the object. So it's extremely sensitive to the inclination. And in the catalog, they assume the same F factor for all quasars. So this is what leads the mass segregation that I showed here to you. So not necessarily these double peaked are more massive than non-double peaked. It's just because they use only one F factor to do the count. So the bias in Eddington ratio basically is attributed to the same reason, because Eddington ratio depends on the bolometric luminosity that does not segregate a lot, and depends on the black hole mass that segregates a lot. So if the mass is strongly segregated because the individual inclination of each object was not considered, the Eddington ratio will also be segregated for the same reason, okay? So these both mass and Eddington ratio are very biased because of the inclination. About bolometric luminosity. So let's move this. Since the dominant part of the quasar luminosity comes from the accretion disk, we should expect a decrease in luminosity with the increase of the inclination. So we expected that non-double peaked sample to be around 17% higher than double peaked sample in bolometric luminosity. And with the catalog values of the bolometric luminosity, we found that the difference was 12%. And it could be attributed to the inclination, but the uncertainty is very large, so we cannot conclude this for sure. And I would like to highlight here that in the catalog, bolometric luminosity was estimated using an approximation based on a specific part of the continuum. This part is the region around this wavelength here. So it may not reflect the entire continuum, but this region. So to investigate if this behavior remains the same across the whole continuum, we decided to catch another spectral region and estimate the bolometric luminosity from this another region. So the chosen region was this region around this wavelength here, which belongs to the big blue bump. So in my opinion, it reflects the accretion disk better than this another region. And when we calculated the bolometric luminosity from this region, it showed much more segregation than the first one. The difference between the non-double peaked and double peaked sample was almost 40%. So we were expecting 17 and we observed 38. So we conclude that inclination is not the only reason of this segregation. and that something else must be contributing to it. But what is this something else? So we decided to study eigenvector 1 parameter of our objects, which is basically the main sequence of the quasars. And because the interpretation of this parameter here is related to accretion rate of the quasars, where objects in this region tend to have higher Eddington ratio, while objects in this another region here tend to have lower Eddington ratio. So as we can see in our sample, our DP objects are in the low Eddington ratio region, while our DP objects are well distributed in higher and lower Eddington ratio values. So in the previous slide, I said that inclination alone could not explain how much the bolometric luminosity decreases from one subsample to another, and adding the Eddington ratio to this explanation fills the gap that we need. So our conclusion is that inclination plus Eddington ratio lead all the trends that we find. So let me see. I don't think we have, I think that we don't have much time, so I will not go into individual explanations for each change, but the combination of inclination and Eddington ratio seems to explain well all the trends that we found. And here I show an example of how spectral properties of the broadline region emission lines segregate among our subsamples, but this segregation is not restricted to the broadline region. Eddington ratio and inclination may create a bias in all regions of the quasar. For example, here, I can show to you that even in the narrow line region, the physical and spectral properties are affected by some bias. And this bias can also be explained by a combination of inclination and Eddington ratio. Here, we also have the behavior of Arion 2 complex emission line and the radial properties, which are also segregated, and we can explain with the same combination, Eddington ratio plus inclination. But as I said before, it would take too much time to explain individually how much the inclination, how much the Eddington ratio should affect this bias. But in our paper that we will publish it soon, everything is well explained. Okay. Just a second. So, continuing. Since our subsample selection was based on an inclination model, we expect a certain number of objects in each group. So in non-double peaked group, we found the expected number of the objects. So we expect 30% of our sample should be non-double peaked, and we observed this. But to the other two groups, it was not confirmed. And the reason for this discrepancy is here. Here I show to you some examples of quasars from Charlotte Ward's paper, which are highly inclined, but they have an additional component attributed to the broadline region winds. And this additional component here makes the emission line shape very similar to the one that we used for the intermediate sample, shifting some objects from DP group into intermediate group in our selection. So this additional component here mask the disk and introduce this bias in our visual selection. So our DP sample are the most inclined ones without this additional component. And in our interpretation, this additional component is associated with higher Eddington ratios. So let's see. Okay. In our second paper, we started to study photometric variability, and to estimate the variability, we choose the FVAR parameter, which measures the relative variability of the brightness with respect to its average brightness. So right after calculating the FVAR, we already noticed that groups were separated again. But now, this time, we did not attribute this segregation to the inclination, because the autocorrelation between Eddington ratio and variability is already well known in the literature. So since our DP sample have lower Eddington ratio, they also tend to be more variable, and that is what we find here. And in the previous paper, we concluded that Eddington ratio and black hole masses were strongly biased. And now, using this empirical relation of Igor Benach that relates Eddington ratio with FVAR, we calculated new Eddington ratio values, and after this, new black hole mass values. And the difference among the samples, between the samples, decreased a lot. So I can say that the bias was removed, at least partial. So this paper, wait.
Can you hear me? I'm afraid I have to ask you to wrap it up because we are out of time.
Okay, can I just finish? It's just this one.
Yeah. Thank you.
Okay, so this paper is still in development, but our main results are here. The correlations with the mass are positive, independent of the method that we use to estimate the mass. We also confirmed that anticorrelation between bolometric luminosity is and FVAR is true. And our strongest correlations were found with the spectral properties of magnesium 2. We don't know why, but there is here. So here was just a summary, and I would thank you all to your attention, and thank Thaisa for supervising me, Panda for